Before the Earth was formed, before the Sun ignited, before galaxies even swirled into existence, there was a single moment, a flashpoint that created time itself. This was the Big Bang, the birth cry of the cosmos. From an unimaginable singularity, the universe erupted into being, creating space, time, matter and energy in the blink of an eye. In those first fleeting seconds, forces beyond comprehension shaped the building blocks of everything we know. The stars, the planets, the atoms that would one day form us. But the story didn't end there. From that chaos emerged order. Stars were born, died, and in their deaths, scattered the seeds of life across the void. Galaxies collided, new worlds formed, and somewhere, on a fragile blue planet orbiting an ordinary star, something extraordinary happened. Life began. This is the story of the universe told from the very beginning. From the birth of atoms to the rise of ancient civilizations who first looked to the stars in wonder, to modern astronomers who pierce the veil of space-time itself. We will journey across the eras of recombination and reionization, through the birth of stars and the creation of galaxies, to the formation of our own solar system, and ultimately to the birth of Earth and the life it sustains. Every atom in your body was forged in the heart of a dying star. Every breath you take connects you to the ancient cosmos. Prepare to witness the greatest story ever told, the story of us, written in the stars. This is Season 1, The Origins of Everything.
In examining the extensive chronology of astronomy, the most appropriate starting point is the inception of space and time. 20th century astronomers, including Edwin Hubble, determined that the universe is expanding by observing that large-scale structures such as galaxies are receding from one another in all directions. This indicates that historically, the universe was more compact, that at a certain moment in the remote past, everything originated from a singular point of space and time, a singularity. Extensive observations by the Hubble Space Telescope and other institutions have demonstrated that the universe originated from an explosion of this singularity approximately 13.7 billion years ago. Cosmologists and astronomers who research the universe's origin and evolution have meticulously examined the specifics of the Big Bang theory through decades of astronomical observations, laboratory experiments, and mathematical modeling. These studies have provided significant insights into the early history of our universe, which is remarkable. In the initial second of the universe's existence, the temperature decreased from 1 quintillion degrees to merely 10 billion degrees, forming all present protons, hydrogen atoms, and neutrons from this primordial plasma. The identical nuclear fusion process that persists today within stars generated helium and other light elements from hydrogen when the universe was merely 3 minutes old. The formation of space and time in a singular moment 13.7 billion years ago is astonishing. What was the cause of the explosion? What existed before the Big Bang? Cosmologists assert that the question is unaskable since the Big Bang originated in time. it is also humbling to acknowledge that the most prevalent element in our bodies, hydrogen, was formed in the initial moment of existence. We are antiquated. Era of Recombination. The nascent universe experienced extreme heat, pressure, and radiation. The fundamental illumination of highly ionized atoms and subatomic particles permeated all of space, engaging in interactions, collisions, decay, and recombination at millions of degrees. This epoch in cosmic history is commonly designated as the radiation era. When the universe reached an age of approximately 10,000 years, the expansion of space and the decay of numerous energetic particles reduced the temperature of the cosmos to roughly 12,000 kelvins, a unit of measurement above absolute zero. This was a significant threshold because as the universe further cooled, the cumulative energy from heat and ionizing radiation diminished below the total rest mass energy of matter. Albert Einstein's renowned equation E equals mc squared exemplifies this concept. For hundreds of thousands of years, the universe remained an opaque, dense, high-energy mixture of continuously colliding ionized protons and electrons. Nonetheless, as the expansion and cooling progressed, the energy of the radiation diminished relative to the residual mass energy. Approximately 400,000 years after the Big Bang, the temperature decreased to a few thousand kelvins, sufficient to facilitate the capture of electrons. This resulted in the formation of stable hydrogen atoms and the aggregation of multiple hydrogen nuclei into the universe's inaugural molecules, hydrogen gas, or H2. This epoch in the universe's primordial history is called the Recombination era. Recombination facilitated decoupling the universe's residual radiation, predominantly high-energy photons and other subatomic particles, from matter, enabling it to traverse space with minimal obstruction. The universe became colder and darker over the subsequent few hundred million years, a period referred to by cosmologists as the Dark Ages. We can still observe the residual 3 Kelvin glow of the liberated radiation energy from the early universe, known as the cosmic microwave background. Each dark age concludes with a renaissance, and the universe's early history is no exception. Cosmologists assert that the Dark Ages lasted approximately 100 to 200 million years. Subsequently, molecular hydrogen and other molecules generated during the recombination epoch commenced to aggregate gravitationally, potentially influenced by turbulence, though the exact cause remains uncertain. The gas clumps functioned as seeds, gravitationally attracting additional gas, resulting in their expansion until they ultimately transformed into vast hydrogen clouds that began to heat internally due to the rising pressure of the surrounding gas. When a cloud experiences a subtle impetus, such as the gravitational pull from an adjacent cloud, it initiates movement and ultimately commences rotation. Approximately 300 to 400 million years post-Big Bang, the temperatures within the cores of certain massive, gradually rotating gas clouds escalated to millions of degrees, akin to those observed during the initial 3 minutes following the Big Bang. The temperatures and pressures within these spherical clouds reached sufficient levels to fuse hydrogen into helium, forming the first stars. The Dark Ages have concluded. The initial stars, often designated population 3 stars by astronomers, were not merely peculiar local phenomena. These colossal stars, potentially 100 to 1,000 times more massive than our Sun, exerted considerable influence on their stellar environment, emitting vast quantities of energy into the surrounding hydrogen clumps and clouds, thereby heating them externally and liberating electrons that were captured during the early Dark Ages. This period is called the Era of Reionization because the universe resumed emitting light, not from the initial creation, but, akin to the present, from the illumination and warmth of stars. Milky Way galaxy. Astronomers define a galaxy as a gravitationally bound assembly of stars, gas, dust, and other enigmatic elements refer to dark matter, all traversing the cosmos collectively as though they were a singular entity. Following the emergence of the initial stars, it was unavoidable that numerous stars would gravitationally draw one another, resulting in clusters, clusters of clusters, and ultimately substantial assemblies of stars orbiting their shared center of gravity. The Milky Way galaxy contains approximately 400 billion stars. Its structure is characteristic of barred spiral galaxies observed across the universe, referred to spiral galaxies. Two smaller galaxies encircle the Milky Way, and a diffuse spherical halo comprising older stars, star clusters, and additional galaxies. The Milky Way features a densely populated central semi-spherical bulge of stars and a flatter spiral disk comprising stars, including the Sun, gas, and dust. It is a colossal structure, approximately 100,000 light-years wide. The distance light traverses in a year, or about a quintillion miles, and 1,000 light-years thick in the disk. The Sun is approximately midway from the galactic center, and one complete orbit around the galaxy takes roughly 250 million Earth years. Astronomers must ascertain the precise formation date of the Milky Way. The halo of the oldest known stars in the galaxy is approximately 13.2 billion years old. The oldest stars in the disk are approximately 8 to 9 billion years old. Although the Milky Way's fundamental structure seemingly formed early, its various components likely developed at distinct intervals. In creation myths, the luminous pale band that pervaded their nocturnal sky inspired wonder in our ancient ancestors, who frequently envisioned it as a river of light and vitality. Despite our understanding that we reside within a vast orchestrated assembly of stars, it remains effortless to experience wonder at the scale and grandeur of our home galaxy. Solar nebula. The process of star formation is chaotic. As massive molecular clouds undergo collapse, nearly all of the gas and dust within the cloud ultimately converge into the central protostar. A small portion of gas and dust persists in orbit around the nascent star. As the entire system rotates and cools, this remaining cloud of debris gradually flattens into a disk composed of gas, dust, and ice, located farther from the star. In this phase of stellar formation, all nascent stars are accompanied by a disk, commonly referred to as a solar nebula disk. The nebula that ultimately gave rise to our Sun likely began its collapse approximately 5 billion years ago, although the precise timing remains uncertain. Observations indicate that Sun-like stars generally require approximately 100 million years for formation, while nebular disks around young stars develop in roughly 1 million years. Upon formation, the disk experiences swift transformations as minuscule dust and ice particles collide, adhere to one another, and develop into marble-sized entities, a phenomenon termed accretion, which computer simulations suggest occurs within a few thousand years. These minuscule particles collide and occasionally adhere to one another. The process appears to continue in a chaotic and unregulated manner until, in approximately a few million years, planetesimals, kilometer-sized aggregates of dusty, icy, rocky, and metallic particles, and subsequently, asteroids ranging from 100 to 1,000 kilometers in size have emerged. Solar nebular disks are ephemeral. The majority of dust either accumulates or disperses within a span of 10 million years. The proximity to the star results in excessive warmth, rendering the planetesimals predominantly rocky and insufficiently massive to retain significant gaseous matter through gravitational forces. In the outer regions, ice and dust can coalesce into larger planetesimals with sufficient mass to accumulate substantial quantities of gas, ultimately evolving into giant planets. The transformation of chaotic origins into refined planetary systems in a brief time frame is presently a subject of considerable discourse and conjecture among astronomers. agitated proto-sun. The formation of stars, akin to childbirth, is a vigorous and chaotic process that demands substantial energy. Before achieving the requisite temperature and density for hydrogen fusion into helium, nascent protostars can release substantial energy as they undergo gravitational contraction throughout their 100 million-year gestation period. Certain nascent stars concentrate their energy into jets comparable in size to the solar system, transporting gas, dust, and charged particles. Intense magnetic fields from the star may heat these jets, material accreting from the associated nebular disk, or a combination of both. Astronomers have observed numerous violent jets of material ejected from nascent protostellar objects, commonly referred to as T Tauri stars, named after the prototype example. Astronomers believe that the star T Taurus resembled the Sun in its youth. This indicates that our star experienced a brief tumultuous phase of vigorous jetting and other high-energy phenomena before initiating stable hydrogen fusion and transitioning into its prolonged, predominantly tranquil existence on the main sequence. Ordinary chondrite meteorites, among the solar system's least favorable materials, may retain evidence regarding whether the Sun experienced a tumultuous early T Tauri phase. These rocks, which periodically descend to Earth, represent the oldest known solids in the solar system and assist in establishing the Sun's age and the timeline for planetary formation. Frequently, these meteorites consist of chondrules, which are diminutive spheres of mineral grains that originated as molten rock droplets that solidified and developed into larger grains, planetesimals, and asteroids. The origin of the energy responsible for chondrule melting in the nascent solar system remains unidentified. However, high-energy eruptions and jets from the young Sun are plausible candidates. As astronomers investigate space with greater depth and precision, they uncover increasing evidence of jets and disks surrounding newly formed stars, indicating that these characteristics are essential to star formation. A tumultuous adolescence may be a fundamental aspect of a conventional star's life cycle. Formation of the Sun. For approximately 100 million years, the temperature and pressure in the core of the solar nebula escalated significantly until they exceeded a threshold. This caused hydrogen atoms to become densely compacted, resulting in nuclear fusion. This transformed them into helium and emitted energy in the form of light and heat. Consequently, our Sun was created. The Sun is often regarded as exceptional, and justifiably so, as it is essential for the genesis and ongoing sustenance of all life on Earth. Although it is challenging to perceive the Sun as typical, average, or even mundane, it is in many respects precisely that. Our star is among over 10 billion trillion, one followed by 22 zeros, stars in the observable universe, all of which seem to be the natural consequence of matter, predominantly hydrogen, interacting with gravity under conditions of high pressure and temperature, thereby emitting vast quantities of energy into the surrounding space. Stars are indeed the powerhouses of our universe. Upon their formation, stars lead stable existences and ultimately perish, frequently in predictable and occasionally dramatic manners. The Sun is analogous. It will continue fusing hydrogen into helium atoms for another 5 billion years. Upon depleting its hydrogen, the Sun expels its outer layers, engulfing the Earth and other inner planets while fusing helium in its core. Upon depleting its helium, the Sun will progressively evolve into a white dwarf, ultimately diminishing into a cinder. Astronomers have determined that in the Milky Way galaxy, approximately 1 to 3 new stars are formed annually, while an equivalent number of old stars perish yearly. Extrapolating to all known galaxies and performing some calculations indicates that approximately 500 million stars are born and 500 million stars perish each day in the universe. It is a profound and humbling realization that should enhance our appreciation for each of these invaluable days in the life of our star, the Sun. Mercury. All planets in our solar system originated approximately 4.5 billion years ago as the solar nebula cooled, condensing minute particles that collided, adhered, and ultimately aggregated into a limited number of substantial bodies. The planets were composed of rock in the thermally favorable region near the Sun. Beyond the now line, mixtures of rock, ice, and gas existed. Mercury is the nearest of the terrestrial planets, possessing a diameter of 3,032 miles, 4,880 kilometers. In contrast, Earth's diameter measures 7,926 miles, 12,756 kilometers. Mercury revolves around the Sun at an average distance of merely 0.38 astronomical units, AU. 1 AU equals 93 million miles equals 150 million kilometers equals average orbital distance from the Sun. The Romans designated Mercury to honor the Greek deity Hermes, renowned for his swift messengers. The planet was aptly named. Even the ancients recognized that Mercury requires merely 88 days to complete its orbit around the Sun. Mercury is a diminutive planet marked by severe extremes and intriguing mysteries. The absence of an atmosphere results in temperature fluctuations from 90 kelvins in permanently shadowed polar craters to over 700 kelvins in intense midday sunlight, exceeding the melting point of lead. Radar observations from Earth suggest the presence of ice in the polar craters. Mercury possesses a notably high density and a substantial iron core comprising 75% of its radius. The core may be partially molten, which accounts for Mercury's feeble magnetic field, measuring only 1% of Earth's strength. Photographs from the two space missions that have approached Mercury, Mariner 10 in 1974 to 1975 and Messenger in 2011 to 2015, exhibit a surface marked by numerous craters and indications of primordial volcanic activity akin to the Moon. Notably, the planet contains a system of substantial tectonic thrust faults, scarps, suggesting that Mercury may have been molten in its early history and contracted by several percent upon cooling. Venus. It is intriguing to contemplate the significance of nature versus nurture in shaping personalities and traits. Twins serve as excellent case studies. This also holds true for planets, with Venus serving as a prime example. It is similar to Earth in certain aspects, yet markedly distinct in others. Venus is approximately 5% smaller than Earth and possesses a similar density, indicating that it is a rocky terrestrial planet akin to ours. Both planets possess atmospheres, and Venus orbits within the same vicinity of the inner solar system as Earth, at an average distance of 0.72 astronomical units compared to Earth's 1.0. However, that is where the resemblances conclude. Venus rotates slowly, completing one axial rotation in approximately 243 Earth days, counterclockwise. The atmosphere of Venus is significantly denser than that of Earth, exhibiting a surface pressure 90 times greater. The dense atmosphere exhibits turbulent upper-level wind velocities exceeding 218 miles, 350 kilometers per hour. The atmosphere predominantly comprises carbon dioxide, with minimal traces of nitrogen dioxide, oxygen, and water. The carbon dioxide molecule is impervious to visible light. Nonetheless, it is exceptionally effective at capturing heat radiation, like a greenhouse, resulting in a surface temperature on Venus exceeding 750 kelvins, or approximately 300 degrees hotter than an oven. Astronomers are investigating the reasons behind the stark contrast in surface conditions between Earth and Venus. Comprehending carbon dioxide could be pivotal. Earth's oceans absorb carbon dioxide, sequestering it in mineralized carbonate formations. Any ocean on primordial Venus, being marginally closer to the Sun, would have evaporated, resulting in no mechanisms to eliminate carbon dioxide. Venus exemplifies the severe consequences of carbon dioxide and illustrates how examining other planets can yield insights into possible futures for Earth. Planet Earth. Earth is the largest of the terrestrial planets and the sole one possessing a significant natural satellite. Geologists assert that the rocky volcanic planet has divided its interior into a thin, low-density crust, a thicker silicate mantle, and a high-density, partially molten iron core. An atmospheric scientist states that it is a planet characterized by a tenuous atmosphere of nitrogen, oxygen, and water vapor. The atmosphere is encircled by a vast expanse of liquid water and polar ice caps, which contribute to significant climatic alterations occurring over seasonal to geological timescales. To a biologist, it is paradise. Earth is the sole location in the universe that harbors life. Fossil and geochemical records indicate that life on Earth commenced almost immediately after the cessation of the late heavy bombardment of asteroids and meteorites. The conditions on Earth's surface have remained comparatively stable for the past 4 billion years, and coupled with its advantageous position in the habitable zone, where temperatures are moderate and water is liquid, this has facilitated the flourishing and evolution of diverse life forms. A multitude of shifting tectonic plates adrift on the upper mantle, partition Earth's crust. Dynamic geological phenomena, earthquakes, volcanoes, mountains, and trenches, transpire at plate boundaries. Most of the oceanic crust, 70% of the surface area, is relatively young, having emerged from mid-ocean ridge volcanoes from a few 100 million years ago to the present. Owing to its youth, merely a few hundred impact craters persist on our surface, starkly contrasting the heavily eroded visage of our neighbor, the Moon. Elevated levels of oxygen, ozone, and methane in the atmosphere indicate life that extraterrestrial astronomers observing our planet remotely might discern. These gases are precisely what astronomers seek among the many newly discovered extrasolar planets. Are there potentially undiscovered Earth-like planets awaiting exploration? Mars. We may need to look no further than the nearest planet to ascertain the existence of life or its past existence beyond Earth. Since antiquity, when Mars was perceived as a celestial embodiment of the Roman god of war, to the 20th century, when it was envisioned as the residence of Percival Lowell's forlorn canal constructors, Mars has consistently captivated human interest. Mars is a diminutive planet, approximately half the diameter of Earth and merely 15% of its volume. The surface area of Mars is approximately equivalent to that of all Earth's continents combined. On average, the planet orbits approximately 50% farther from the Sun than Earth. The tenuous Martian atmosphere, composed primarily of carbon dioxide and only 1% as dense as Earth's, cannot retain significant heat, resulting in a frigid surface temperature. Daytime temperatures near the equator seldom exceed the freezing point of water, while nighttime temperatures near the poles consistently fall to the freezing point of carbon dioxide, 150 kelvins, approximately minus 190 degrees Fahrenheit. Currently, Mars is a barren planet in a state of extreme cold. Spacecraft imagery, Martian meteorites, and various data collected over nearly 5 decades indicate that Mars is the most Earth-like location in the solar system, apart from Earth itself, and that during its initial few billion years, the red planet may have possessed a significantly warmer and more humid environment. What transpired? Potential causes encompass the gradual cooling of the planet's core, solar wind, or the catastrophic impact obliterating the atmosphere. Investigating the mechanisms and reasons behind the planet's significant climatic changes is a prominent area of research. Approximately 3 to 4 billion years ago, we acquired sufficient knowledge about Mars to ascertain that certain regions of its surface and subsurface were conducive to life. The forthcoming 50 years of Mars exploration will focus on broadening the quest for habitable environments and determining whether any have been or currently are inhabited. Principal asteroid belt. Approximately 4.5 billion years ago, diminutive rocky and metallic constituents termed planetesimals rapidly coalesced into terrestrial planets within the solar nebula's gradually cooling, warmer inner regions. Each developing planet accumulated planetesimals along and adjacent to its orbital trajectory, typically clearing its orbital zones until the depletion of new material to collect imposed a constraint on the expansion of these terrestrial bodies. The substantial gravitational pull of nearby Jupiter consistently impeded and interrupted the accretion of planetesimals and their development into larger planets beyond Mars's orbit. The influence intensified collisions between planetesimals, reducing the frequency of gentle impacts and facilitating their aggregation and growth. In the Mars-Jupiter region, proximate interactions with Jupiter expelled numerous planetesimals. Consequently, rather than a substantial planet between Mars and Jupiter, we possess a relatively diffuse disk or belt of minor rocky and metallic asteroids, the main asteroid belt. Astronomers estimate there may be over 1 million asteroids exceeding half a mile, approximately 1 kilometer, in the main belt. More than 500,000 of these celestial bodies have their orbits, positions, and general characteristics documented, including the two most massive Ceres and Vesta. These two, along with the asteroids Pallas and Juno, constitute over 50% of the total mass of the entire main belt. Asteroids are not arbitrarily positioned. The gravitational pull has eliminated numerous gaps in the main belt, referred to Kirkwood gaps, and certain groups of asteroids move in unison as families, which may signify the fragmented and gradually dispersing remnants of formerly larger entities. The asteroids of Jupiter and the Trojans constitute two significant clusters of small celestial bodies ensnared in unique orbits where the gravitational forces of Jupiter and the Sun are in equilibrium. Fragments of impact-shattered asteroid interiors frequently descend to Earth, becoming meteorites. Their ages and compositions yield extensive insights into the timing, formation, and evolution of our solar system. On August 14, 2006, a computer-generated diagram depicted the inner solar system reaching Jupiter's orbit, the outer blue circle, with the Sun at its center. Asteroids in the main belt exhibit a white coloration. The orange dots represent the Hilda asteroid family, while the green dots signify Jupiter's Trojan asteroids. Jupiter. The solar system consists of the Sun, approximately 99.8%, Jupiter, approximately 0.1%, and all other celestial bodies. Jupiter, the largest planet, possesses twice the mass of all the other planets combined. 63 identified moons and tenuous rings revolve around this immense planet. Jupiter's diameter equals 23 Earths. If it were hollow, it could accommodate over 1,000 Earths. Due to its vast size and its orbital location at the inner boundary of the outer solar system, approximately 5.2 astronomical units, Jupiter ranks as the fourth brightest object in the night sky, following the Sun, Moon, and Venus. Jupiter is luminous due to its bright, cloud-covered surface. Indeed, no surface is discernible on Jupiter or any other colossal outer planet. All observable phenomena consist of a cloud or haze composed of exotic and occasionally vibrant chemical compounds such as methane, ethane, ammonium hydrosulfide, and phosphine. Winds exceeding several hundred miles per hour distort clouds into horizontal bands, while colossal storm systems like the Great Red Spot have persisted for centuries. Below the clouds, Jupiter's pressure and temperature rise significantly, yet the chemical composition is comparatively simpler. Jupiter consists of approximately 75% hydrogen and 25% helium, akin to the Sun. Had the solar nebula been larger and Jupiter formed with approximately 50 to 80 times its current mass, it would have evolved into a star. Jupiter's formation significantly impacted the solar system's architecture, disrupting the orbits of other giant planets, inhibiting planet formation in the main asteroid belt, and gravitationally scattering asteroids and comets into orbits that resulted in impacts with other planets during the late heavy bombardment. Jupiter has ejected certain objects completely into the Kuiper belt or beyond the solar system. Jupiter serves as a gravity formation, capturing small celestial bodies like comet SL9, which fragmented and collided with its atmospheric layers in 1994. Saturn. For an astronomy enthusiast, observing Saturn and its magnificent rings through a small telescope may be the most captivating experience. The scene is nearly surreal, a luminous egg-shaped orb suspended in the void of space, encircled by an exceptionally far-eyed, slender disk of material nearly twice the planet's diameter. It is genuinely one of the celestial jewels. Saturn is the second largest gas giant, exceeding Earth in width by more than 9 times and in mass by nearly 100 times. The renowned ring of Saturn is the planar disk that encircles the planet's equator. The ring system, primarily comprised of ice, is likely between 22 and 33 yards, 20 to 30 meters, thick. The origin of Saturn's rings remains uncertain. They may be an ancient primordial characteristic or a more recent formation of a former icy moon. Saturn is accompanied by 62 recognized moons, numerous smaller moonlets within its rings, and billions of ring particles that vary in size from houses and cars to mere specks of dust. Titan, Saturn's largest moon, surpasses Mercury in size and is the sole moon in the solar system, possessing a dense atmosphere. Despite a similar atmospheric composition, the clouds and haze bands are less vivid and less colorful than those of Jupiter. The primary chemical distinction between Saturn and Jupiter is that, for reasons not entirely comprehended, Saturn possesses a slightly lower helium-to-hydrogen ratio, rendering it less solar than Jupiter. Another enigma is the significantly higher wind speeds on Saturn than Jupiter or any other location in the solar system, exceeding 1,120 miles per hour in certain areas. Comprehensive investigations of Saturn and Jupiter, conducted by the Pioneer, Voyager, Galileo, and Cassini spacecraft, reveal that gas giants exhibit significant variability. As we identify additional gas giants among extrasolar planets, these worlds are expected to be both beautiful and mysterious. Uranus. In contrast to the initial 6, the 7th planet of our solar system was unknown to ancient civilizations. In 1781, the English astronomer Sir William Herschel identified Uranus via telescopic observations. Numerous astronomers had detected Uranus as early as 1690, yet they erroneously identified it as a star because of its swift movement across the sky, an orbital period of 84 years. Uranus, with an average orbital distance of approximately 19 astronomical units, effectively doubled the size of the solar system upon its discovery, in contrast to Saturn's average orbital distance of about 9.5, a diameter 4 times that of Earth, and a mass 15 times that of Jupiter, is categorized as a giant planet. However, it is significantly smaller than its planetary counterparts, Jupiter and Saturn. The atmosphere of Uranus predominantly comprises hydrogen and helium, while methane imparts the planet's characteristic blue-green hue and contributes to the hazes in the upper atmosphere. Storms on Uranus are infrequent, and the cloud and haze bands are typically subtle. Uranus possesses a distinct planetary composition compared to Jupiter and Saturn, containing substantial quantities of ice and rock within its deep interior. Uranus and Neptune possesses a markedly greater proportion of ice and rock relative to gas compared to Jupiter and Saturn, categorizing the planet as an ice giant rather than a gas giant. Telescopic observations and the Voyager 2 flyby in 1986 revealed that Uranus has 5 large moons and 22 smaller moons, all of which are dark and icy. The planet features approximately 12 slender, dark, icy rings, likely resulting from the recent disintegration of one or more minor moons. Uranus's distinctive axial tilt is approximately 98 degrees relative to the ecliptic, the Earth's orbital plane around the Sun. An ancient grazing giant impact or a close encounter with Jupiter may have resulted in Uranus's atypical axial tilt. Regardless of the circumstances, it remains another enigma of our solar system. Neptune. If Earth and Venus are regarded as fraternal twin planets, then Uranus and Neptune resemble identical twins. Both are inhabitants of the distant outer solar system, with Neptune located at 30 astronomical units and requiring approximately 165 Earth years to complete one orbit around the Sun. Both ice giants possess comparable dimensions and mass, with Neptune being marginally more massive at 17 times that of Earth. Their compositions are also analogous, comprising approximately 80% hydrogen, 19% helium, and trace quantities of methane and other hydrocarbons. Methane imparts a striking azure hue to Neptune, similar to its effect on Uranus. Neptune, like Uranus, is an ice giant characterized by a limited quantity of icy satellites, 13, and a system of dark, icy rings. Through telescopic measurements, data from the 1989 Voyager 2 flyby, and laboratory studies, astronomers have determined that Neptune's atmosphere reaches approximately 10 to 20% of the distance to the planet's core. Subsequently, with the rise in pressure and temperature, elevated water, ammonia, and methane concentrations generate a heated liquid mantle. Astronomers refer to this region as icy due to its composition. The molecules are believed to have originated from predominantly icy outer solar nebula planetesimals that contributed to the formation of Neptune. Certain astronomers conceptualize this region as a water-ammonia ocean, and computational models indicate that precipitation of diamonds descends through it to the planet's core, composed of rock, iron, and nickel. Astronomers are perplexed by the presence of ice giants in the distant outer solar system, as there may have been insufficient solar nebula material at those distances for their formation. One explanation is that they originated nearer to the Sun and gradually migrated outward, influenced gravitationally by Jupiter and Saturn. Currently, we view the solar system as stable and orderly. However, during the formation of the planets, it was markedly more tumultuous and chaotic. The Kuiper belt and Pluto. Most of the rock and ice from the solar nebula that did not accrete into the nascent Sun ultimately contributed to the formation of Jupiter and, to a lesser degree, the other large planets in our solar system. Nonetheless, certain residual building blocks, including the diminutive 0.6 to 6 miles, 1 to 10 kilometers, rocky planetesimals in the primary asteroid belt, which Jupiter inhibited from developing into fully formed planets, as well as analogous icy bodies beyond Neptune that were excessively distant and infrequently collided to evolve into substantial planets, persisted. The latter category of trans-Neptunian objects is particularly noteworthy, primarily because the first one ever identified is also the most renowned, Pluto. Pluto is a diminutive, frigid, rocky celestial body in an elliptical orbit ranging from 30 to 50 astronomical units, AU. It constitutes approximately 20% of the Moon's mass and 35% of its volume. It possesses a substantial icy moon, Charon, in addition to at least 4 smaller icy moons and a tenuous cometary atmosphere comprised of nitrogen, methane, and carbon monoxide. Since the early 1990s, astronomers have identified numerous additional celestial bodies akin to Pluto and Neptune within a toroidal region known as the Kuiper Belt, named after the Dutch-American astronomer Gerard P. Kuiper. Beyond the Kuiper Belt, where small icy bodies originated in the region between approximately 30 and 55 astronomical units, another scattered disk comprises icy bodies that formed nearer to the Sun, but were ejected to distances ranging from 30 to 100 astronomical units due to gravitational interactions with Jupiter. Over 1,100 trans-Neptunian objects have been identified. In 2006, the International Astronomical Union reclassified Pluto and similar celestial bodies to dwarf planet status, as it became evident that numerous Pluto-like objects exist in the Kuiper Belt and scattered disks. A space mission has not yet explored Pluto, our solar system's final prominent celestial body. In 2015, the New Horizons mission will alter perceptions by flying past Pluto and its moons, unveiling them as distinct celestial bodies rather than mere indistinct points of light. Formation of the Moon. Earth is distinctive among terrestrial planets due to its substantial natural satellite. What is the origin of our Moon? Astronomers have contemplated numerous potential concepts. One hypothesis posits that the Moon originated in orbit around Earth concurrently, and through a similar process as Earth's formation, via the accretion of rocky and metallic planetesimals that coalesced from the heated inner solar nebula. Another hypothesis posits that the primordial, molten Earth was rotating at such a high velocity that a portion of it detached, fissioned, and entered orbit, resulting in the formation of the Moon. Another hypothesis posits that the Moon originated from a distinct location within the inner solar system, which was subsequently captured by Earth. These theories vied for dominance until the Apollo missions returned lunar rocks and additional data to Earth, demonstrating the necessity of aligning with the empirical evidence regarding the Moon. The co-accretion model anticipated that the Moon would share a similar age and composition with Earth. However, this is not the case. The Moon exhibits significantly lower density and reduced iron content, and seems to have formed 30 to 50 million years after the formation of Earth and other planets. Fission induced excessive rotation of the primordial Earth, while the capture model proposed that it was impossible to dissipate all the energy that a freely orbiting Moon would have expended. In the 1990s, planetary scientists proposed the giant impact hypothesis, positing that a Mars-sized protoplanet may have collided obliquely with the primordial Earth, sufficiently melting a portion of Earth's iron-deficient mantle to propel it into orbit, where it would subsequently cool, accrete, and ultimately form the Moon. The Moon's composition, density, and age corresponded with the models. The giant impact hypothesis remains the most compelling explanation for the Moon's origin. Late heavy bombardment. All planets, including Earth, have endured a significant influx of asteroids and comets throughout geological history, with the impact rate in the early solar system being vastly greater than it is today. The Earth does not retain a record of its early cosmic impact history because younger volcanic deposits obscure much of the surface, and erosion from wind, water, and ice has further diminished these records. Conversely, the Moon's surface is significantly more illustrative, with the extensive array of lunar impact craters and basins as a poignant reminder of Earth's tumultuous past. A significant legacy of the Apollo missions is the capacity to ascertain the absolute ages of particular impact cratering events through the radioactive dating of lunar samples. The study discloses the dates of notable lunar impact occurrences. 3.8 to 4.1 billion years BCE, a remarkable finding given that all the principal planets coalesced approximately 4.5 billion years ago. Numerous planetary scientists contend that the most straightforward explanation is that the Moon, and by extension Earth, experienced significant impact cratering approximately 400 to 700 million years following their formation. The cause of this brief uptick in a rate that typically declined remains uncertain. However, some speculate that Jupiter's gravitational influence may have redirected certain asteroids and comets into the inner solar system. This is the identical force that may have prompted the movement of Uranus and Neptune, and likely propelled trans-Neptunian objects into the Kuiper belt. If accurate, the ensuing cataclysm undoubtedly devastated the terrestrial planets and significantly impacted the evolution and stability of life on Earth. Existence on Earth. The origins of life on Earth remain ambiguous regarding the how, when, or why, yet it emerged almost instantaneously. We deduce that the most ancient life indicators on Earth are chemical evidence rather than fossils, as all known life exhibits a shared chemical structure. Notably, patterns are observable in the isotopes of carbon and certain other elements due to the biogeochemical processes and reactions that all terrestrial life undergoes. Reactions involving amino acids prevalent in DNA or RNA generate these patterns. Essentially, life utilizes and generates specific materials. The 3.8 billion-year-old rocks from Greenland exhibit a higher concentration of carbon-12 relative to carbon-13. Though it remains contentious, this constitutes chemofossil evidence for early life on Earth's surface. The oldest known fossil evidence of microbial life on Earth is approximately 3.5 billion years old. To conserve it, primitive organisms such as blue-green algae accumulate layers of ancient stromatolites, rocks, and mineral formations. Stromatolites continue to develop in locations like Shark Bay in Western Australia, rendering them some of Earth's most ancient life forms. Recent research on the Hadean epoch, 4.5 to 3.8 billion years ago, indicates that oceans and continents may have developed significantly earlier than previously believed, and conditions may have been conducive to life merely a few 100 million years post-formation of our planet. Between 3.8 and 4.1 billion years ago, the late heavy bombardment may have eradicated earlier life forms or hindered their development. Regardless of the circumstances, shortly after Earth's cooling, the oceans emerged, the late heavy bombardment concluded, and Earth attained sufficient stability to sustain life. It flourished and commenced expansion into numerous niches, which is noteworthy. Astronomers, planetary scientists, and astrobiologists are currently seeking evidence of life on other Earth-like planets. This is a cross-sectional representation of a stromatolite fossil. The reddish strata are thought to be the fossilized remnants of primordial blue-green algae, representing some of the planet's most ancient preserved evidence of life. This specimen, originating from the Ord Range in Western Australia, measures approximately 2.4 inches, 6 cm. Cambrian explosion. The initial life forms to appear on Earth were uncomplicated, unicellular microbes capable of harnessing chemical and thermal energy from the primordial environment. Single-celled organisms, sometimes forming colonies like those in stromatolites, predominated on Earth for 3 billion years. The diversity of life on Earth significantly increased approximately 550 million years ago, a phenomenon called the Cambrian explosion. Consequently, numerous ancestors of contemporary flora and fauna emerge relatively early in the geological fossil record. Biologists discuss potential explanations for the abrupt and significant diversification of life at the Precambrian/Cambrian boundary. Biologists are investigating the causes of numerous abrupt and significant declines in species and species diversity in the fossil record. The most significant event transpired at the juncture of the Permian and Triassic geological periods, approximately 250 million years ago. Approximately 70% of terrestrial and 96% of marine species perished over roughly 1 million years, a duration informally referred to as the Great Dying and the mother of all mass extinctions. It required over 100 million years for the biodiversity of life on Earth to attain pre-Permian levels once more. climate may have precipitated a significant loss of life on Earth, although many contend that the speed of this occurrence is challenging to elucidate. Alternatively, a catastrophe such as a significant impact event or a massive volcanic eruption, which may have also instigated additional climatic and geological disasters, could be accountable. Biologists, geologists, and astronomers continue to seek evidence. The Permian extinction, occurring 250 million years ago, significantly reduced Earth's species and biodiversity. The perspective from Yavapai Point over the Grand Canyon reveals nearly 2 billion years of Earth's geological history for meticulous examination. 65 million years ago. Impact causing dinosaur extinction. In collaboration with their colleagues Luis and Walter Alvarez, a father-son geological duo, have discovered evidence indicating that a significant asteroid impact on Earth likely caused the extinction of dinosaurs and many other species around 65 million years ago. A significant discovery was a thin layer of sediment globally enriched with the rare element iridium, dated to the KT boundary, which demarcates the Cretaceous and Tertiary geological periods. Iridium is a platinum metal that is frequently associated with iron formations. During its formation, a significant portion of Earth's iridium descended into the deep mantle and core. Therefore, a globally distributed, iridium-rich crustal deposit of identical age is an anomaly. The Alvarez hypothesis posits that iridium originated from a substantial metal-rich asteroid colliding with Earth, resulting in vaporization and significant climatic alterations, severely affecting plant and animal species. The impact propelled vaporized rock and dust into the atmosphere, igniting extensive fires that released soot and smoke, obscuring the sun and reducing global surface temperatures for years. While the impact was less profound than the Permian-Triassic extinction, the KT boundary obliterated species dependent on sunlight and photosynthesis, undermining the foundations of numerous predator-prey lineages. The event did not significantly impact certain species, including mammals and birds that can burrow or rely on insects, carrion, or other non-wood-based food sources. Once the dust settled, the survivors could exploit niches previously inaccessible to them. Researchers are continually evaluating the hypothesis that an asteroid impact led to the extinction of the dinosaurs. Additional geological and climatic factors, including a significant decline in sea levels or extensive volcanic eruptions that transpired concurrently but before the proposed impact, may have influenced the environmental conditions that led to the extinction of numerous species. Homo sapiens. Homo sapiens is a comparatively recent species of human on Earth. Fossil evidence from African archaeological sites indicates that our earliest emergence occurred approximately 200,000 years ago. Fossil evidence indicates that Homo sapiens coexisted with the closely related subspecies Neanderthals, with Neanderthal traits vanishing from the record approximately 30,000 years ago. We thrive in survival by utilizing tools, language, extensive memory, and acquired experience. Our historical progression illustrates a profound curiosity, yearning for intangible soul sustenance, potentially elucidating the significance of music, dance, and art in the human experience. I recall observing the 17,000-year-old Paleolithic cave paintings from the Dordogne region of France, and being astonished that our ancestors could allocate time for art despite their incessant struggle for survival. Nevertheless, they ought to have devoted greater attention to animals, plants, and other quotidian matters daily. A growing number of archaeologists contend that certain dots, lines, and potentially animal figures served as representations of constellations or other celestial features. These are the oldest paintings on Earth and celestial maps produced by the earliest explorers. The emergence of humanity represents a negligible milestone in the annals of astronomy. We are one species on a single planet, revolving around a commonplace star in a relatively unremarkable region of an average spiral galaxy. Our planet may be one of the billions capable of sustaining life, and we could be one of the innumerable sentient species in the cosmos. However, we may also be the sole intelligent, self-aware, technological species and civilization in the cosmos. The latter possibility is both humbling and daunting, potentially even frightening. It serves as a reminder that we ought to celebrate the emergence of a species that, through its accomplishments, enables the universe to comprehend itself. Impact of Arizona. Asteroid and comet impacts have struck the Earth throughout history. We need only examine the record of the late heavy bombardment retained on the ancient, airless surface of our celestial neighbor, the Moon. Due to the obliteration of impact craters on Earth by persistent erosion from wind and water, as well as the ongoing renewal of the seafloor through plate tectonics and volcanism, it is unsurprising that terrestrial geologists took considerable time to acknowledge the significance of impact cratering as a geological process on Earth and other terrestrial planets, moons, and asteroids. The meteor crater, also known as the Barringer crater or Canyon Diablo crater, located east of Flagstaff, Arizona, is an exemplary natural laboratory for this understanding. The crater measures approximately 1,200 meters, 3,900 feet, in width, and 170 meters, 557 feet, in depth. Until the 1960s, geologists vigorously contested the origin of this feature. During the 1890s, G. K. Gilbert, an early proponent of the impact hypothesis for the circular craters on the Moon, contended that the absence of substantial debris from the impactor indicated that an explosive volcanic event created the crater. In the early 20th century, mining engineer Daniel Barringer acquired the crater and devoted years to drilling, convinced that a colossal buried iron meteorite from an impact event lay beneath. Geologist Eugene M. Shoemaker, who examined craters created by the U.S. government's program in Nevada, verified that the crater resulted from an impact. This was primarily due to his discovery of quartz mineral varieties that could exclusively develop in an impact's high-pressure, high-temperature conditions rather than a volcanic setting. Since then, scientists have identified over 200 additional impact craters on Earth, the majority of which are larger yet considerably less well-preserved than meteor crater. Research in impact physics and computational studies has demonstrated that impactors, such as this 164-foot 50-meter iron-rich asteroid traveling at over 6 miles 10 kilometers per second, invariably disintegrate entirely upon collision. This elucidates the absence of debris surrounding the crater, the emergence of cosmology. The Greek term cosmos translates to the universe. Consequently, the contemporary term cosmology pertains to examining the universe's essence and development. In a classical context, a society's cost embodies its worldview regarding its origins, purpose, and future. Throughout history, civilizations have developed and sustained their cosmologies via creation narratives, mythology, religion, philosophy, and more recently, science. It is common to encounter clichés regarding humanity's perennial fascination with the stars or the contemplation of the heavens by our ancient ancestors. Although observing is enjoyable, comprehending the thoughts of prehistoric individuals is unattainable due to the absence of historical records. The oldest archaeological artifacts depicting astronomical themes are significant as they offer tangible evidence for comprehending ancient perspectives on the universe. The earliest extant evidence of a civilization contemplating the cosmos originates from the Sumerians in their incomplete star maps or fragments of rudimentary astronomical instruments, which some scholars estimate to be 5,000 and 7,000 years old. The limited information from that era demonstrates considerable sophistication in the Sumerians' comprehension of the movements of the sun, moon, major planets, and stars. Perhaps unsurprising that the Sumerians established the first city-states, sustained by a permanent sedentary population engaged in agriculture. Understanding celestial patterns directly correlated with planting, irrigation, and harvesting timing. A reliable food supply allowed them to develop writing, arithmetic, geometry, and algebra. Sumerian cosmology was the inaugural system to deify celestial bodies, a tradition subsequently adopted by Babylonian, Greek, Roman, and other cosmologists. Sumerian cosmology advocated the concept of multiple heavens and earths within a distinctly non-geocentric universe. This world aligns with contemporary cosmological theories, suggesting a universe devoid of a center and teeming with numerous Earths. Antiquated astronomical observatories. Although ancient civilizations recognized the sky, substantial monuments with astronomical themes emerged only during the Bronze Age, approximately 3000 to 600 BCE. The most renowned of these is the prehistoric monument of Stonehenge in southern England, which represents one of numerous ancient stone circles, burial mounds, and other earthwork structures globally, possessing cultural, religious, and astronomical significance. The cobblestones of Stonehenge are remarkable, particularly the 25-ton lintel stones positioned atop the 13-foot, 4-meter, 50-ton standing post stones. Contemporary experiments and simulations have demonstrated that constructing such structures was feasible with Neolithic and Bronze Age tools and techniques. Neither supernatural forces nor architecturally skilled extraterrestrials were necessary. It likely approached the limits of the existing technology to construct such unparalleled structures. It is a remarkable achievement in prehistoric design. Some archaeologists assert that the configuration of diverse sites, post holes, pits, paths, and ridges at Stonehenge indicates its function as an astronomical observatory. It is believed to be partially constructed as a colossal sundial to monitor the shifting seasons and ascertain the precise timing of the winter and summer solstices. Archaeologists and astronomers largely concur that the monument's fundamental alignment was conceived with the trajectories of the sun and moon in consideration, although the specifics of its utilization remain a topic of ongoing research and discussion. Additional instances of ancient astronomical observatories include the Newgrange and Maeshowe burial mounds in Ireland and Scotland, designed to illuminate the interior tombs solely with the rising sun during the winter solstice. The solar-aligned trilithons and passage mounds in Portugal, and the stacked Taula stones on the Spanish island of Minorca. 5,000 years ago, the civilizations that constructed these extraordinary monuments did not leave any written documentation regarding their identities, customs, or beliefs. Nonetheless, they preserved enduring records in stone and earth, indicating the significance they attributed to their understanding of the cosmos. Astronomy of ancient Egypt. The colossal pyramids of Giza exemplify ancient Egyptian civilization's technological and labor management capabilities. They also demonstrate the expertise of designers and astrologers who played a significant role in Egyptian society and religion 4,500 years ago. Due to Earth's rotation and wobbling motion akin to a spinning top, Polaris was not the North Star in 2500 BCE. Similar to the current skies near the South Celestial Pole, there was no prominent star near the North Celestial Pole during that time. To the pharaohs, astrologers, and commoners, the nocturnal sky seemed to revolve around a vortex-like dark void believed to be an entrance to the heavens. This gateway was approximately 30 degrees above the northern horizon in ancient Egypt. Consequently, they meticulously oriented the pyramids towards the north, and a narrow shaft extended from the pharaoh's primary chamber to the exterior, aimed directly at the center of the gateway. If the objective was to unite with the deities in the afterlife, why not enter through the primary entrance? Egyptian astrologers contributed substantially to developing a sophisticated and established calendar system during the construction of the pyramid. The commencement of a new year was marked by the initial appearance of the luminescent star Sirius, Sopdet to the Egyptians, shortly before dawn in midsummer. The year was segmented into 12 months, each comprising 30 days, with an additional 5 days allocated for religious observances or festivities, resulting in a total of 365 days. Upon meticulous observation and documentation of stellar positions on various dates, they recognized the necessity of incorporating an additional day every 4th year, a leap day, to maintain the alignment of their calendar with celestial movements. They monitored the pre-dawn rising times of numerous luminous stars to organize significant religious festivals and anticipate the annual inundations of the Nile. The pyramid form may symbolize an aspect of ancient Egyptian cosmology, as certain myths assert that the creator god, Atum, resided within a pyramid that arose from the primordial ocean alongside the land. The colossal pyramids of Giza were the preeminent human-made edifices globally for almost 4,000 years. They served as burial sites for the pharaohs and as astronomical indicators of the hypothesized portal to the heavens at the northern celestial pole. Astronomy in China. Astronomy was independently cultivated and utilized across various global cultures. Archaeological evidence from ancient burial sites indicates that the origins of Chinese astronomy can be traced to the prehistoric and Bronze Ages through the preservation of star and constellation nomenclature. Similar to previous and subsequent civilizations, the early Chinese possessed a profound awareness of the cycles and movements of the sun, moon, and stars. Each prominent dynasty of early China enlisted astronomers to develop complex solar and lunar calendar systems. They were meticulous and contemplative in their astronomical observations, systematically documenting evidence of celestial changes, including solar and lunar eclipses, sunspots, planetary motions, and the emergence of new comets or supernovae. Astronomers utilized distinctive records maintained by Chinese astronomers from the Xia, Shang, and Zhou dynasties, approximately 2100 to 250 BCE, for historical astronomical investigations. Chinese astronomers devised innovative and precise instruments for celestial observation, including extensive celestial globes and armillary spheres employed to chart stars and constellations and monitor the movements and luminosities of planets, guest stars, Chas comet, and novae. Until the 17th century, Chinese astronomers employed advanced versions of these instruments to formulate theories of planetary motion that competed with those created by Western astronomers such as Tycho Brahe and Johannes Kepler, who utilized analogous methods. The ancient Chinese developed multiple intricate cosmological models of the universe. Certain models conceptualize the heavens as a dome or celestial sphere, akin to early Western cosmology, whereas others perceived the heavens as boundless and somewhat chaotic. Before its popularity in the West, certain early Chinese astronomers inferred that the moon and other celestial entities were spherical. The perspective conflict with the dominant perception of a flat Earth appeared inconsequential, as early Chinese astronomical inquiries aligned with the established principles and practices of Confucianism, focused on meticulous observations of the universe as it existed, or at least as it seemed. The Earth is spherical. Pythagoras, 570 to 495 BCE. We frequently underestimate the Earth's beauty as a blue, spherical orb contrasted with the void of space. However, in the absence of the recent advantage of space exploration and observation, someone needed to propose the notion that the Earth could be spherical rather than flat, as it appears to an observer on the surface. Numerous accounts attribute that identity to Pythagoras of Samos, a 6th century BCE philosopher, mathematician, and occasional astronomer from Greece, renowned for his Pythagorean theorem in geometry. Evidence supporting the Earth's spherical shape is the curved shadow it projects onto the moon during a lunar eclipse, exemplified by the event witnessed in Greece. The rationale presented by Pythagoras and his disciples for a spherical Earth was indirect, relying on diverse observations. Sailors journeying south from Greece observed southern constellations ascending in the sky as they progressed southward. Expeditions to locations along the African coast south of the equator indicated that the sun emanated from the north instead of the south, as observed in Greece. The observation of lunar eclipses yielded additional significant evidence. When the full moon aligns directly behind the Earth about the sun, the Earth's curvature becomes apparent as it obscures the moon. The question of whether Pythagoras genuinely discovered the spherical nature of the yearly served as the most vocal and renowned proponent of a concept that was increasingly accepted among the educated elite of early Greek civilization remains contentious. Nonetheless, Eratosthenes' experiments would validate the matter approximately 250 years later, and nearly 2,500 years thereafter. The inaugural astronauts to exit Earth's orbit during the Apollo 8 mission would present to the world the first magnificent images of our beautiful spherical blue planet in space. Our valuable blue planet is a spherical body of rock and metal, enveloped by a thin atmosphere and in numerous locations, liquid water. Our remote ancestors were oblivious to the Earth's spherical shape. Greek geocentrism. Plato, 427 to 347 BCE, and Aristotle, 384 to 322 BCE. Ancient Greece established numerous significant legacies that profoundly influenced Western civilization for millennia. Plato, a mathematician and philosopher, and his student Aristotle, who excelled in various arts and sciences, significantly influenced a cosmological perspective during the classical era. Contemporary Western philosophy and science, encompassing physics and astronomy, are fundamentally rooted in the works of Plato and Aristotle. The primary emphasis of ancient Greek astronomical thought and science overall was to pursue mathematical and physical explanations and models for observed phenomena. It was instinctive to seek solutions through the geometry and trigonometry developed by Pythagoras. Plato employed geometry to partition the universe into two domains: the stationary sphere of the Earth and the concentric, perpetually moving spheres of the Sun, Moon, 5 recognized planets, and known stars, all of which orbited a static Earth. Aristotle included the element ether in the cosmic region beyond the sublunary sphere, the area between Earth and the Moon comprised of the fundamental elements earth, water, air, and fire, believing it formed the rotating celestial spheres that housed the stars and planets. The geocentric perspective of the universe was a significant aspect of Greek cosmology. Moreover, the pursuit of symmetry and simplicity suggested that celestial spheres ought to exhibit uniform circular motions or their combinations, an interpretation aligned with the prevailing astronomical data. Nevertheless, Plato's model accounts for all observed celestial motions. In the Roman Empire, the Egyptian astronomer Ptolemy advanced the notion of ideal circular motions. Subsequent astronomers would contest it until the 17th century, when Copernicus and Kepler's empirical and theoretical contributions definitively discredited the geocentric model. Western astrology. Ptolemy, in conjunction with Alexander the Great, 356 to 323 BCE, astrology posits that the positions and movements of the sun, moon, planets, and stars at an individual's birth or other pivotal moments affect or determine human and terrestrial affairs. Numerous civilizations throughout human history have embraced some variant of this belief. Certain scholars assert that the origins of Western astrology trace back to the earliest documentation of Sumerian cosmology in the 6th millennium BCE, when priests sought celestial signs to discern the god's will, refer to birth of cosmology. Astrology has evolved into its contemporary form. The Greeks evolved astrology from its origins as a tool for priests and kings in Babylon to comprehend celestial influences on agricultural success, warfare, or other significant matters into a personal endeavor. Crafting horoscopes for individuals, from monarchs to commoners, about both historical and trivial events. Alexander the Great, a Greek monarch who studied under Aristotle, was a pivotal figure in advancing astronomy, establishing and governing a vast empire that spanned from northern Africa to the Mediterranean and the Middle East. Alexander founded the preeminent educational institution at the illustrious Library of Alexandria in Egypt, marking the inception of horoscopic astrology. The Egyptian astronomer Ptolemy notably established the 12 classical zodiac constellations over subsequent centuries and delineated the fundamental functions and roles of the planets across various scientific disciplines, including astronomy, medicine, and zoology. Ptolemy's geocentric, astrology-based cosmology would shape and prevail in Western astronomical thought for more than 1,300 years. In the contemporary world, belief in astrology is an easily dismissible concept. Nevertheless, newspapers continue to publish daily horoscope columns. Many individuals continue to seek counsel from contemporary astrologers, or at the very least from astrological websites, regarding guidance and purported forecasts concerning their futures. Perhaps it is mere amusement, yet an aspect of human nature craves this illusory order in the universe. Heliocentric universe Aristarchus, 310 to 230 BCE. The geocentric model proposed by Plato and Aristotle influenced ancient Greek cosmological thought. What is the reason for this? It was evident that the sun, moon, and stars revolved around the Earth. Researchers presented additional purportedly incontrovertible evidence. The moon exhibited phases aligning with Earth's orbit. Why does nothing detach from the Earth's surface despite its axial rotation? The stars exhibited no parallax or displacement relative to other stars, as if the Earth were stationary in its orbit. The case is concluded. Nonetheless, there existed doubters and skeptics. Aristarchus, an astronomer and mathematician from the Greek island of Samos, is the earliest documented figure. He contested his esteemed Greek colleagues' nearly 200-year-old conventional wisdom by conducting meticulous naked-eye observations of the sun and moon and attempting to interpret them within a geocentric framework, human perspective. Nonetheless, his comprehension of the human eye constrained his methodologies. However, he inferred through geometrical calculations that the sun was at least 20 times more distant than the moon. The actual distance is 400 times. He concluded that since the sun and moon possess approximately equivalent apparent angular diameters in the sky, the sun's size must be at least 20 times greater than that of the moon and 7 times larger than that of the Earth. Therefore, based on his reasoning, the sun's volume was over 300 times that of the Earth. The actual value is approximately 1 million. He must have deemed it ludicrous that a colossal sun would be tethered to a comparatively minuscule planet like Earth instead of the opposite. He posited that Earth and other planets revolve around the sun, and asserted that parallax is unfeasible due to the considerable distance of the stars. Aristarchus's cosmos was significantly more expansive than previously depicted by others. As with many revolutionary concepts, Aristarchus's heliocentric theory was met with ridicule and disdain by his contemporaries. 250 years later, Ptolemy's geocentric doctrines and writings effectively suppressed the notion. Aristarchus instilled a seed of skepticism that would flourish in the 16th century. Eratosthenes calculates the Earth's circumference. Plato, 427 to 347 BCE, Aristotle, 384 to 322 BCE, and Eratosthenes, 276 to 195 BCE. The Greeks commonly acknowledge the Earth's spherical shape, dating back to the era of Pythagoras, although estimations of its precise dimensions differed significantly. Plato estimated the Earth's circumference at approximately 44,000 miles, 70,000 kilometers, implying a diameter of about 14,000 miles, 22,000 kilometers, while Archimedes approximated a circumference of around 34,000 miles, 55,000 kilometers, and a diameter of 109,000 miles, 17,500 kilometers. To achieve a more precise assessment, Eratosthenes, a mathematician, astronomer, and the third chief librarian of Alexandria, formulated a straightforward experiment resembling using the Earth as a colossal sundial. Eratosthenes discovered that at noon on the summer solstice in the southern Egyptian city of Syene, the sun was nearly directly overhead at the zenith, resulting in vertical posts casting no shadows. He was aware that in his city of Alexandria, located in northern Egypt, vertical posts cast diminutive shadows at noon during the summer solstice. He conducted measurements and ascertained that the sun was slightly more than 7 degrees south of the zenith in Alexandria. This equates to approximately 1/50th of a circle's circumference, leading him to deduce that the Earth's circumference was roughly 50 times the distance between Alexandria and Syene. He estimated the Earth's circumference at approximately 250,000 stadia, or 25,000 miles, 40,000 kilometers, based on a distance of roughly 5,000 stadia between Alexandria and Syene, where the stadium was an ancient Egyptian and Greek unit of measurement. Assuming a stadium measured approximately 175 yards, 160 meters, from Eratosthenes results in a circumference of approximately 25,000 miles, 40,000 kilometers, which is fundamentally accurate considering the various uncertainties and assumptions inherent in the measurements. Eratosthenes is widely regarded as the father of geography for having coined the term. He was the inaugural individual to ascertain the Earth's dimensions with precision. His approach exemplifies the efficacy of a straightforward, well-timed experiment. Archimedes once inquired about levers. "Provide me a fulcrum, and I shall move the earth." Eratosthenes could have readily replied, "Provide me with a few rods and some shadows, and I shall measure the earth." Hipparchus, 190 to 120 BCE, is a figure associated with stellar magnitude. Certain stars exhibit brightness, while others display dimness. Individuals observing a clear night sky can ascertain this, yet until the mid-2nd century BCE, no one had attempted to measure its luminosity. Hipparchus, the Greek astronomer and mathematician, created the inaugural comprehensive star catalogue. Hipparchus established a magnitude scale for stars, ranging from 1 for the 20 brightest stars to 6 for the faintest stars visible to the naked eye, each increment representing a brightness perceived as half that of the preceding level. Contemporary astronomers continue to employ a brightness scale derived from Hipparchus's original, albeit with some modifications. In the mid-19th century, they recalibrated the magnitude system, establishing that each increment was 2.5 times brighter or dimmer than the preceding one. They extended the scale beyond 6 steps and correlated it with the luminosity of the star Vega, which is designated with a magnitude of 0. We designated negative magnitudes to luminous stars, planets, the moon, and the sun. Simultaneously, we extended the maximum magnitude threshold to 30 for exceedingly faint stars observable solely with the most sophisticated telescopes globally. Despite the apparent peculiarity of dimmer stars possessing higher magnitudes, astronomers have adapted to this system that has existed for over 2,100 years. Hipparchus developed trigonometry, identified the precession of the Earth's rotational axis, and achieved the most precise measurements of the relative positions of bright stars, astrometry. Acknowledging his exceptional observational abilities, a space astrometry satellite launched in 1989 was named in his honor. Initial computing device. Approximately at the conclusion of the 1st century BCE, a Roman vessel transporting a substantial collection of ancient Greek artifacts submerged in the Mediterranean near the Greek island of Antikythera. In 1901, 2 millennia later, divers encountered the wreck and uncovered among the artifacts the deteriorated remnants of what is potentially the world's oldest computer, referred to as the Antikythera mechanism. Initially, archaeologists hypothesized that the mechanism could be a mechanical clock due to its numerous small gears. The craftsmanship, akin to the mechanical clockwork of 17th century Europe, would render this an extraordinary discovery in its own right. Nevertheless, extensive cleaning and further research over the decades have demonstrated that the device is far more than a mere clock. It appears to have operated as an intricate mechanical astronomical computer and calendar, proficient in calculating the historical and forthcoming positions of the sun, moon, and planets, forecasting eclipses, and illustrating the phases of the moon. It is the most ancient example of an orrery, predating others by 1,500 years, and is a meticulously designed and constructed clockwork model of the solar system. The revelations regarding this device are extraordinary on multiple fronts. The ancient Greeks demonstrated an exceptionally accurate and detailed understanding of planetary motions, including nuanced fluctuations in the moon's velocity every month. The perfectly operating mechanism suggests the creation of multiple devices, and their small size denotes their intended portability. In 1901, an ancient Greek shipwreck produced one of the remaining fragments. In contemporary society, we are familiar with the intricate relationship between technological progress and scientific breakthroughs. Thus, it is unsurprising that this phenomenon also existed in ancient Greco-Roman eras. It is humbling and startling to uncover evidence from a solitary artifact indicating that civilization was significantly more technologically advanced than previously assumed. Julian calendar, Julius Caesar, 100 to 44 BCE. Like previous civilizations that observed the heavens, the Romans established a calendar system with significant astronomical ties. Initially conceived in the 8th century BCE, the resultant confusion owing to its synthesis of components derived from the Greeks and their antecedents. The year comprised 10 months, each containing either 30 or 31 days, amounting to 304 days. The system disregarded the additional 61 days necessary for a complete orbit around the Sun, designating them as winter. A subsequent modification introduced 2 new winter months, January and February. Yet the total remained at only 355 days per year. The high priests periodically inserted an intercalary month to align the calendar with the seasons. Nonetheless, adding extra days to a specific year was frequently arbitrary and politically driven. The situation became so chaotic that numerous ordinary Romans were unaware of the day, year, or month. Upon ascending to power in 49 BCE, Julius Caesar reformed the Roman calendar system, which was in disarray, to better synchronize it with solar movements rather than human activities. Julius Caesar extended several months, resulting in a total of 365 days in a year. He also mandated that every 4th year, an additional leap day would be appended to the conclusion of February, resulting in an average year length of 365.25 days, approximating the true duration of a solar year, 365.242 days. Caesar's calendar reform was implemented on January 1st, 45 BCE, or in Roman terms, 709 years post-Rome's founding, following the priests' adjustment of the year 46 BCE to 445 days to rectify prior discrepancies. The Julian calendar functioned effectively for an extended period, deviating from the true solar year by merely 0.008 days, approximately 11 minutes annually. By the 16th century, those 11 minutes annually had resulted in a notable discrepancy between the calendar year and the solar year. Consequently, an additional modification, the Gregorian calendar reform, was necessary to align the calendar with the seasons. Ptolemy's Almagest, Ptolemy, 168 CE. For approximately 700 years, circa 300 BCE, 400 CE, The vast library of Alexandria in Egypt served as the intellectual hub of the world. The renowned Greek and Roman scholars we honor today, who advanced mathematics, astronomy, and other disciplines, either visited or worked there, supervising an extraordinary collection of hundreds of thousands of scrolls and books. The Egyptian mathematician and astronomer Claudius Ptolemy, published the Almagest, the preeminent work in classical astronomy, approximately 150 years ago. Ptolemy was a comprehensive scientist. He proficiently operated numerous astronomical instruments and conducted significant observations. His paramount ability lies in curating and integrating the contributions of his predecessors from the past 800 years to create a unified, comprehensive perspective of the cosmos within a single volume. The Almagest was segmented into 13 distinct sections. One of them provided a comprehensive elucidation of Ptolemy's geocentric cosmology. This theory was founded on the concepts that Plato, Aristotle, and others initially posited. The orbits of the planets were described as small circles, epicycles, that were subsequently situated within larger circles, deferents, with the Earth positioned at the center. The system was intricate. However, fundamentally, the stars and planets traversed exclusively along perfect spherical or circular trajectories, exhibiting beauty and symmetry that aligned with the available data and likely resonated with Ptolemy as appropriate for the work of an ideal creator. The book contained convenient tables for calculating the risings and settings of celestial bodies, alongside chapters addressing the general motions of the sun, moon, and planets, eclipses, precession, and observational instruments. Hipparchus's star catalog and the stellar magnitude system were the foundation for an extensive catalog of over 1,000 stars, a tubular system. Regrettably, Ptolemy's overarching perspective of the solar system was incorrect. Nevertheless, due to its continued proficiency in elucidating and forecasting celestial movements, the Almagest and its geocentric model of the universe would persist as the authoritative source of astronomical knowledge for more than a millennium. View guest star in Chinese. Ancient Chinese astronomers were diligent observers of the heavens. Historians have observed that official Chinese astronomy research was frequently conducted by full-time, court-appointed civil servants rather than individual scholars. This demonstrates a significantly more systematic and comprehensive method of observing the skies for alterations than their Roman, Greek, or Babylonian predecessors and counterparts. Consequently, the Chinese meticulously observed and recorded any novel celestial phenomena, integrating these findings into the imperial dynastic annals, many of which still endure. An exemplary instance was the abrupt emergence of what they termed a guest star in the southern skies in the year 185. Chinese astronomers documented this occurrence as a significant event in the extant records of the Eastern Han Dynasty, 25 to 220 CE. Notwithstanding the absence of illustrations, contemporary astronomers were persuaded that the Chinese had conducted the initial documented observations of a supernova. Contemporary optical, radio, and X-ray telescopes at that location reveal a semi-spherical gaseous nebula designated as RCW86. This nebula appears to be the remnants of a stellar explosion over 1,800 years ago. This is a contemporary perspective of the remnants of supernova explosion 185. Ancient Chinese astronomical illustrations, which remain extant, documented numerous additional guests. Notable are illustrations depicting objects with a luminous spherical head and one or more feathery or spiky tails. The Chinese designated these objects as broom stars. Contemporary interpretations often regard them as brilliant comets with extensive gas and dust tails. Notable comets recorded by Chinese astronomers in 240 BCE and 12 BCE, along with those in 141, 684, and 837 CE, are likely to represent observations of the same comet, ultimately identified in 1682 as Halley's Comet, which has a periodicity of 76 years. Early Chinese astronomers' diligent and systematic observations of the sky, along with their precise record-keeping, have become valuable resources for historians and astronomers. Aryabhatiya. In India, as in many other ancient civilizations, the foundations of astronomy significantly impacted the evolution of religion. Astronomical knowledge constituted the basis of early calendar systems that determined dates for Hindu religious observances and seasonal agricultural activities. Similar to the West, advancements in instrumentation employed by clerics and early astronomers for mapping the positions of the sun, moon, and stars resulted in the formulation of more intricate cosmological models for elucidating and forecasting celestial movements. Aryabhata, a mathematician and astronomer, was the inaugural prominent thinker to significantly advance the field of astronomy in India. He authored the oldest extant Indian treatise on mathematics and astronomy, the Aryabhatiya, published circa 500 CE. Aryabhata concisely encapsulated all mathematics in verse form in the Aryabhatiya and incorporated useful new tables for trigonometric computations. Aryabhata elucidated eclipses in the astronomy sections of the Aryabhatiya as the rational consequence of shadows cast by the earth or the moon rather than attributing them to celestial demons. Employing his newly devised spherical trigonometry calculations and eclipse measurements, he determined the Earth's circumference with an accuracy of less than 0.2% of its true value, markedly enhancing Eratosthenes' prior best estimate from 750 years earlier. Aryabhata's most revolutionary assertion was that the Earth is not stationary in space, but rotates on its axis, while the stars in the celestial sphere remain fixed. The Indian cosmology during Aryabhata's era was unequivocally geocentric. Simultaneously, his precise calculations of planetary positions depended on orbits and epicycles akin to those in Ptolemy's Almagest. Aryabhata was the first to propose elliptical paths for the planets instead of circular ones. Scholarly interpretations of the Aryabhatiya suggest that Aryabhata posited a heliocentric cosmos. Nonetheless, akin to Aristarchus in Greece, these radical heliocentric concepts would require over a millennium to gain acceptance in India. Locating Easter. Numerous global religions commemorate specific feast days and holidays on dates that fluctuate based on seasonal changes, lunar phases, the position of particular stars, or other astronomical phenomena not anchored to the calendar. Consequently, priests, monks, and other religious authorities who forecasted these occurrences frequently needed a comprehensive understanding of contemporary astronomy and mathematics. The timing of Easter, the Christian commemoration of Christ's resurrection, is arguably one of the most perplexing of the world's principal movable religious holidays to ascertain. Easter is theoretically observed on the first Sunday after the full moon following the vernal equinox. In practice, predicting the date of the full moon or lunar equinox was so perplexing that medieval astronomers coined a specific term to denote the calculation of the calendar date of Easter each year: computus. Various types of computers were utilized during the early Middle Ages, each corresponding to a distinct Easter date. A monk named Bede of Jarrow, originating from the Kingdom of Northumbria in present-day northern England and Scotland, proposed a standardized computer in the early 8th century. He elucidated and extensively disseminated it in his works On Time and On the Reckoning of Time. Bede's computus and astronomical education enabled him to ascertain that the date of Easter follows a 532-year cycle, comprising 19-year lunar and 28-year solar cycles. Ultimately, he was able to ascertain the date of the most important Christian holiday of the year. Bede's computing abilities and expertise as a historian and theologian garnered him the title Venerable Bede. His writings significantly influenced the Middle Ages by elucidating various practical calculations related to solar, lunar, and tidal calendars. He even estimated the Earth's age using the Book of Genesis. He proposed 3,952 BCE, close to the 4004 BCE estimate, popularized in the 17th century by Anglican Archbishop James Ussher. Preliminary Islamic astronomy. Medieval Islam saw a prolonged period of brilliance and innovation in the arts and sciences, which significantly contributed to the contemporary language and methodologies of astronomy and mathematics. However, scientific advancement in Europe stagnated during this period, resulting in the Persian and Arab worlds becoming the principal inheritors of the Greco-Roman legacy in astronomy and mathematics. Among the notable early Islamic astronomers and mathematicians who made significant contributions were Al-Khwarizm, who established modern algebra, al-Jabr meaning completion in Arabic, and devised innovative techniques for calculating the positions of the sun, moon, and planets. Al-Hasib, who provided the most accurate estimates for the diameter and distance of the moon and the diameter of the sun, compiling his findings in the Book of Bodies and Distances. Al-Batan, who refined Ptolemy's Almagest and developed new methods for timing the moon's first appearance, and Al-Birun, who created new astronomical instruments and observational techniques, and, along with several other Persian and Arabic astronomers, proposed that a heliocentric model of the solar system could accommodate the available observational data as effectively as the prevailing geocentric model. The contributions of these and other Islamic astronomers from the Middle Ages influenced Western astronomers during the Renaissance, including Brahe, Kepler, Copernicus, and Galileo. This resulted in the dismissal of Ptolemaic geocentrism in favor of heliocentric cosmology. Moreover, nearly all prominent astronomers and mathematicians of early Islam collaborated in teams within the inaugural research groups, constituting the first system of state-sponsored observatories and research institutions. Islamic scientists have made substantial progress in astronomy and other disciplines due to this collaborative environment, which is the foundation for contemporary scientific practices. Andromeda observed. A significant early astronomer from the Arab world was Abd al-Rahman al-Sufi of Persia, present-day Iran. Like many other medieval astronomers, Al-Sufi possessed knowledge of the principal elements of classical Greek astronomy and cosmology, including Ptolemy's Almagest, which he translated into Arabic. He and others aimed to elaborate on Ptolemy's concepts and integrate them with novel observations and theories from early Arabic astronomy, exemplified by the Book of Fixed Stars, a seminal work. Al-Sufi's book primarily comprised a comprehensive chart of the stars within the 48 classical Greek constellations recognized in that period. It utilized stellar data from Ptolemy's earlier catalog in the Almagest and Hipparchus's stellar magnitude system, but it was enhanced or rectified by incorporating his and other contemporary observations of stellar brightness and color. The Book of Fixed Stars employs Arabic nomenclature for the prominent stars within each constellation. Numerous star names such as Altair, Betelgeuse, Deneb, Rigel, and Vega remain in contemporary usage. In the segment of Al-Sufi's book concerning the constellations Andromeda and Pisces, he observes a small cloud identified among the prominent stars. Although he could not have anticipated it, Al-Sufi is generally regarded as the first individual to document the Andromeda galaxy, the closest spiral galaxy to the Milky Way, situated approximately 2 million light-years away. Designated as Messier Object 31, Andromeda is approximately 8 times larger than the full moon. The moon is exceedingly dim, necessitating exceptional vision and patience for detection. Al-Sufi was the inaugural observer of additional dim star clusters, nebulae, and clouds, including one of the Milky Way's subtle elliptical companion galaxies in the southern hemisphere. 550 years later, Europeans prominently recognized and popularized this object, designating it the Large Magellanic Cloud about Ferdinand's circumnavigation of the globe in 1519. Ancient Greek scholars primarily focused on philosophical or theoretical aspects of science, particularly astronomy. Conversely, the Arabic approach to astronomy and mathematics that prevailed during the Middle Ages emphasized the invention of novel instruments and methodologies, the acquisition of new observations, and the application of data to formulate innovative solutions for practical religious and societal requirements. This methodology was novel: observe, document, analyze, interpret, hypothesize, and reiterate. It demonstrated significant efficacy and constitutes the foundation of the contemporary scientific method. Several notable Arab and Persian mathematicians at the onset of the first millennium CE established the groundwork for this novel, observationally oriented methodology for comprehending the cosmos. Abd al-Hassan ibn al-Haytham was a Muslim physicist and mathematician renowned for his expertise across various disciplines. He championed empirical experimentation and rigorous testing of established theories, opposing reliance on conjecture or natural philosophy, and criticized Ptolemy. In his Book of Optics, he stated, "In all our endeavors, our objective should be balanced, not capricious, the pursuit of truth, not the endorsement of opinions." Concurrently, the Persian scholar Abu al-Rayhan al-Birun, well versed in various physical and social sciences, advocated for a comparable experimental approach in astronomy and other disciplines. He formulated innovative methodologies, such as replicating experiments and analyzing random and systematic error in the outcomes. "I do not reject the truth regardless of its origin," he stated in his extensive scientific work, Kitab al-Qanun al-Masadi. Al-Haytham, al-Birun, and numerous other polymaths of the Middle Ages can be regarded as the world's inaugural scientists, dedicated to observation and exploration across diverse disciplines, skeptical of unverified assertions, and inherently self-reflective. For over a millennium, these characteristics have benefited scientists significantly. Astronomy of the Maya civilization. In addition to Europeans and Asians, other cultures also engaged in the study and practice of astronomy during prehistoric times and the Middle Ages. A sophisticated astronomical tradition developed in Mesoamerica, originating as early as 2000 BCE within advanced indigenous civilizations such as the Maya, Olmec, Toltec, Mississippian, and other associated cultures. Nevertheless, these civilizations produced scant written documentation, partly owing to the loss or destruction of numerous records during subsequent European conquests. Only 4 extant texts are available to evaluate the scientific knowledge of the Mayan civilization, which flourished from approximately 2000 BCE to 900 CE. The Dresden Codex, named for its current repository, is a significant manuscript from the late period of Mayan history, just before European contact. It offers compelling evidence that Mayan astronomy attained a level of advancement and sophistication comparable to that of the Greeks, Arabs, and other early civilizations. The Dresden Codex encompasses both historical and mythological elements. Nonetheless, it consists of comprehensive astronomical tables for charting and forecasting the movements of the Sun, Moon, Venus, and other recognized planets. Upon deciphering the glyphs and numerals, archaeoastronomers discovered that the 74 pages of illustrated tables depict the cycles of Venus. Every 584 days it rises and sets anew, and the Moon. 8 lunar cycles recur every 25,377 days. The Mayans, who identified the distinct repeating eclipse cycles with greater accuracy than their Babylonian and Greek counterparts, could also utilize the tables to forecast eclipses. They could also forecast lunar and planetary conjunctions with remarkable precision. Understanding these celestial periodicities with such precision necessitated centuries of meticulous observations and advanced instruments. Upon discovering the cycles, the Mayans utilized the tables to perpetually predict celestial events. How did the Mayans utilize this information? Although much is still enigmatic, historians have recognized numerous possible religious, agricultural, social, and military events and traditions associated with their astronomically based calendar system. By the conclusion of the early Middle Ages, various societies had thriving or emerging communities of astronomers and mathematicians attuned to the celestial realm. In 1054, a new star and significantly emerged in the Taurus constellation, capturing the attention of numerous societies. Chinese astronomers initially documented the emergence of a guest star on July 4th. Persian, Arab, Japanese, and Korean observers validated their observations, while Native American Anasazi artists documented the event through rock paintings. The Europeans, entrenched in the Dark Ages, failed to document the event. Chinese observers observed the new star during the day for 23 days and at night for 653 days until it diminished. At peak luminosity, it was estimated to reach a magnitude of approximately -6 or -7, surpassing all celestial bodies in brightness except for the sun and moon. It is now understood that medieval astronomers observed a supernova, a violent, catastrophic explosion of a massive progenitor star approximately 6,300 light-years from Earth. This star exhausted its nuclear fusion fuel and subsequently collapsed, releasing a tremendous amount of gravitational energy that expelled its outer layers into space at velocities, potentially reaching 10% of the speed of light. 18th century astronomers first observed the crab-shaped emission nebula of ionized gases, heated by the explosion's shock wave over 650 years after the supernova became invisible. In the late 1960s, radio astronomers identified that the compressed core of the progenitor star had transformed into a rapidly rotating neutron star or pulsar, spinning at 30 revolutions per second, measuring approximately 12 miles in diameter, yet possessing a mass 1.5 to 2 times that of the Sun. The meticulous documentation by early astronomers of this phenomenon facilitated identifying the previously unrecognized connection among supernovae, emission nebulae, and neutron stars. The gradual emergence of Western Europe from the Dark Ages coincided with the establishment of the world's inaugural universities in Bologna and Oxford towards the conclusion of the 11th century. The establishment of additional higher education institutions required scholarly works to function as student textbooks. In medieval Europe, printing books was costly and laborious, resulting in the proliferation of only a limited number of standard textbooks in specific disciplines. The English monk and astronomer John of Sacro Bosco published De Sphæra in 1230, which became the inaugural standard astronomy textbook in Western Europe. Sacro Bosco instructed at the University of Paris and held a firm belief in Ptolemaic cosmology. A significant portion of De Sphæra constitutes a summary and critique of the Almagest. Nevertheless, the text integrates contemporary concepts and findings from Arabic astronomy, an evolving discipline of experimental astronomy that surpassed European astronomy during the Middle Ages. De Sphæra examined Ptolemy, incorporating illustrations of celestial spheres and circles, the rising and setting times and positions of prominent stars and the Sun, and elucidations of the Sun's and planets' movements through Ptolemy's epicycle and various models. The work was intended to instruct students on the utilization of an armillary sphere. Sacro Bosco unequivocally established that the Earth is a spherical entity and offered precise elucidations for solar and lunar eclipses. Had a bestseller list for medieval literature existed, De Sphæra would have occupied a prominent position for centuries. From the 13th to the 15th centuries, numerous copies annually transcribed, hundreds of manuscripts remain extant today, and after the release of the inaugural printed edition in 1472, over 90 editions were published in the subsequent 200 years. Historians indicated reading was mandatory in university astronomy courses until the 17th century. Astronomical observatories are often perceived as contemporary creations. Vast domes situated on elevated mountains, colossal telescopes, and advanced computer technology. However, the notion of the observatory as a research institution and a collaborative access facility for groups of astronomers can be traced back to the initial observatories founded in the Islamic world and China during the Middle Ages. The Margay Observatory in northwestern Iran was among the earliest significant observatories globally, founded in 1259 by the Mongol ruler Hulagu Khan, a grandson of Genghis Khan, and overseen by his court astronomer and mathematician Nasser al-Din al-Tusi. Maragay contained an extensive library exceeding 40,000 volumes, and Altis directed a group of astronomers and scholars to conduct observations and computations of planetary movements and Earth's precession, which Copernicus and others would subsequently utilize as essential contributions to a novel heliocentric cosmology. Concurrently, Hulagu's sibling Kublai Khan founded the Gaocheng Astronomical Observatory, marking it as the inaugural facility in China. During the early Yuan dynasty, 1279 to 1368, astronomers conducted observations of the sun and planets. They employed a colossal stone sundial to measure time and, more precisely, ascertain the year. In 1420, the Timurid astronomer and mathematician Ulugh Beg founded a university and observatory in Samarkand, present-day Uzbekistan, motivated by the obliterated Margay. A colossal stone sextant meridian circle, measuring 131 feet, 40 meters in radius, was hewn into the mountainside, making it the largest globally. It was utilized to precisely ascertain the positions of the sun and stars. The Samarkand Observatory, subsequently known as Ulugh Beg Observatory, possessed early astronomical instruments such as astrolabes and armillary spheres. Astronomers at Ulugh Beg revised the star catalogues of Ptolemy and Al-Sufi to incorporate precession, facilitating consistently precise predictions of eclipses and other astronomical phenomena. Astronomical research in India during the Middle Ages was initially grounded in the early discoveries and writings of Aryabhata and other mathematicians and astronomers. It was subsequently augmented by the establishment of specialized research and educational institutions, such as the Kerala School of Astronomy and Mathematics, founded in the 14th century by the mathematician Madhavan of Sangamagramam. Madhavan and subsequent Kerala mathematicians, such as N. Lakantha Somayaji, developed mathematical methods to ascertain planetary motion. Initially, they employed geometry and trigonometry. However, they developed novel methodologies utilizing functions to represent intricate curves and shapes in mathematics. Among these shapes were parabolas, hyperbolas, and ellipses. Their research on ellipses was particularly significant to astronomy, as it validated Aryabhata's prior hypothesis that elliptical orbits could elucidate planetary motion. The innovative mathematical techniques established in Kerala concentrated on a sequence of functions which represented preliminary forms of calculus, preceding the European advancement of calculus by approximately 200 years, notably by scientists such as Isaac Newton. Lakantha's work, Aryabhatyabhasya, a commentary on Aryabhata's Aryabhatiya, published circa 1500, demonstrated that the planetary orbits could be more accurately elucidated by a partially heliocentric solar system and a rotating Earth. In his model, Mercury, Venus, Mars, Jupiter, and Saturn revolved around the Sun, while the Sun revolved around the Earth. The 16th century Danish astronomer Tycho Brahe embraced a comparable model, and certain elements of Nalakantha's framework correspond with the entirely heliocentric cosmology posited by Polish astronomer Nicolaus Copernicus in 1543. The contributions of the Kerala school and Indian mathematics and astronomy more broadly were previously undervalued by the West. The Kerala school, and potentially Indian mathematics and astronomy as a whole, must be regarded as foundational influences underpinning the subsequent discoveries of Copernicus, Newton, and others. Following almost a millennium of stagnation, the Renaissance in Western Europe represented a genuine resurgence in art, music, culture, and science. The founding of universities in Bologna, Oxford, Cambridge, Paris, Padua, and other sites, coupled with the contributions of Arabic, Chinese, and Indian scholars in astronomy during Europe's Dark Ages and the revival of Greek and Roman texts, facilitated the advancement of European science. The foremost and arguably most significant Renaissance scientist to emerge was Nicholas Copernicus, a Polish canon, his uncle, a bishop and patron, physician, lawyer, economist, and occasional astronomer. As a community leader in Frombork, northwestern Poland, Copernicus undertook numerous legal, administrative, and economic duties as part of his official role. He also allocated time for astronomical observations and data analysis, engaged with classical and contemporary astronomical literature, and contemplated issues he had encountered since his studies at Krakow and Bologna, about what he perceived as the excessively intricate geocentric planetary orbit model presented in Ptolemy's Almagest. By 1514, he was disseminating the fundamental framework of an paradigm, a solar system with the Sun positioned at the center, the Earth and other planets rotating on their axes and orbiting the Sun, while the Moon orbiting the Earth. However, it was not until shortly before he died in 1543 that he ultimately published his theory as De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. The book and its heliocentric thesis elicited minimal interest or controversy then. It required over 50 years, along with the corroborative observations and analyses of Brahe, Kepler, and Galileo, including Galileo's telescope, to reveal that De Revolutionibus had initiated what became recognized as the Copernican revolution in cosmology. Before the 17th century, astronomers relied on superior equipment and exceptional eyesight to conduct optimal naked-eye observations of celestial body movements. Except certain Chinese astronomers, only a limited number recognized the significance of performing extensive, consistent, and systematic celestial observations to improve data accuracy. Tycho Brahe, the Renaissance astronomer and Danish nobleman, may have been the foremost Western exponent of this brute force methodology for minimizing errors in measuring planetary motions. At 1560, Tycho observed a solar eclipse, which sparked his enthusiasm for astronomy. His family's affluence and connections enabled him to pursue that passion and establish premier observation facilities. He delved into cosmology, but rejected Ptolemy's geocentric theory and Copernicus's heliocentric perspective. His meticulous observations of newly discovered comets and a star that emerged in 1572, which Tycho termed nova, persuaded him that the fixed stars were not immutable, and that both they and the planets did not traverse the transparent crystalline spheres proposed by the Ptolemaic and Copernican models. His cosmological model resembled that of Nalakantha from the Kerala school, a geo-heliocentric hybrid wherein all planets, except Earth, revolved around the Sun, while the Sun and Moon revolved around Earth. Tycho established the benchmark for superior observations of planetary movements by employing the finest instruments, maintaining a nearly continuous dataset over several decades, and providing a comprehensive account of the uncertainties in his data. Theorists esteemed his measurements, and he was selective regarding his collaborators. I decided to collaborate with Johannes Kepler, as his remarkable dataset facilitated the discovery of the fundamental laws of planetary motion. Tycho was as eccentric as he was meticulous, losing a portion of his nose in a duel, which he replaced with prosthetics made of copper or silver, and ultimately succumbing to a life of excess at the age of 54. Most individuals perceive a year as comprising 12 months or 365 days, often without further contemplation. Every 4 years, we are reminded that the length of one orbit around the Sun is approximately 365.25 days. The Julian calendar reform of 45 BCE instituted the addition of February 29th as a leap day every 4 years to align Caesar's calendar system with the Earth's orbit around the Sun. The Julian calendar defines a year as the period from one vernal equinox to the next vernal equinox. 365.25 days is approximately 11 minutes too lengthy annually. The precise duration is roughly 365.24237 days. This was of little significance during the Roman Empire. However, 1,500 years later, the calendar date diverged by over 10 days from Caesar's solar or seasonal date. Astronomers determined that the spring equinox occurred around March 11th rather than March 21st. This indicated that the Easter celebration reverted to winter, a situation disfavored by the Catholic Church. The circumstance necessitated a resolution. The calendar reform instituted by Julius Caesar in 45 BCE necessitated a revision. The Roman Catholic Council of Trent resolved to amend Caesar's calendar, altering the leap year frequency from 1 in every 4 years, 0.25, to 97 in every 400 years, 0.2425, by designating only those century years divisible by 400 as leap years. The years 1700, 1800, and 1900 were not leap years. However, 2000 was a leap year. Pope Gregory XIII promulgated the Gregorian calendar on October 15, 1582, after rectifying a tendency on October 4, 1582. The contemporary Gregorian calendar, widely utilized globally, accurately aligns with the Earth's orbital position to within 1 day every 7,600 years, sufficient for the foreseeable future. The Earth's rotation gradually decelerates due to tidal friction, resulting in an incremental increase in a day. Consequently, since 1972, the International Earth Rotation and Reference System Service has periodically incorporated official leap seconds into the world's atomic clocks to maintain synchronization with the gradual alterations in the Earth's rotation and the corresponding changes in apparent solar time. 16th century astronomers recognized that a seemingly ordinary star would periodically erupt, significantly enhancing its luminosity, what Tycho Brahe referred to as a nova. However, no one had ever witnessed a star increase in brightness, decrease, and then increase and decrease again. In 1596 and again in 1609, the Dutch-German pastor and amateur astronomer David Fabricius made his observations of the star Omicron Ceti, commonly referred to as Mira. In 1638, the Dutch astronomer Johannes Holvarta identified Mira as a periodic or pulsating variable star for approximately 330 days. When Fabricius discovered Mira, a magnitude 3 star rapidly diminished in brightness within approximately 1 month, exceeding the human visual threshold of magnitude 6. Astronomers subsequently observed Mira through telescopic means, noting its brightness increase to magnitude 2 and decrease to magnitude 10, representing a variation exceeding 1,700 times in luminosity. Mira is a swollen red giant star approximately 350 times the size of the Sun. If situated in our solar system, it would reach the orbit of Mars. Pulsations are a component of the normal stellar evolution of relatively low-mass stars approaching the end of their lifespans. Approximately 7,000 stars are currently recognized to display pulsations of this nature, with periods spanning from approximately 100 to 1,000 days, collectively termed Mira variables. In 1923, researchers identified Mira within a binary star system, accompanied by a diminutive white dwarf designated Mira B. Recent imagery from the Hubble Space Telescope and Chandra X-ray Observatory reveals that Mira B is gravitationally extracting gas from Mira A, forming a solar nebula-like disk that may be facilitating planet accretion. Mira is a dying star, yet it may facilitate the formation of new planets during its demise. Fabricius and his son Johannes are recognized as the inaugural astronomers who systematically observe sunspots and utilize them to ascertain that the Sun rotates, as anticipated by physicist Johannes Kepler, with a rotation period of approximately 27 days. Astronomers have identified that Mira possesses star spots akin to sunspots, potentially linked to robust magnetic fields in the star's outer layers. Bruno's work on the infinite universe and worlds is captivating. His contemporaries in the 16th century did not broadly endorse the heliocentric model of the solar system advocated by Copernicus in 1543. Ironically, despite the notion that the Earth was not the universe's center, contradicting the scriptures of the 16th century Roman Catholic Church, Copernicus, a church canon, did not attract significant controversy for his perspectives. Others would subsequently inherit that controversy. Giordano Bruno, a late 16th century Italian philosopher, astronomer, and Dominican friar, was one of Copernicanism's earliest and most outspoken proponents. Bruno has been a vocal proponent of unconventional and contentious perspectives regarding science, religion, and natural philosophy. Although not recognized for specific observations, skills, or discoveries, Bruno ultimately embraced a form of non-geocentrism significantly more radical than that proposed by Copernicus. In his 1584 work, Dell'infinito, Universo e Mondi, on the infinite universe and worlds, Bruno proposed that Earth is merely one of an infinite multitude of inhabited planets, orbiting an infinite array of stars, which are analogous to our own Sun. The Church regarded the support of such a vast number of worlds as somewhat heretical. Conversely, Bruno explicitly deemed it heretical, alongside other audacious challenges to fundamental concepts in Christian theology, such as the notion that God is not the focal point of his boundless universe. He was persecuted by the Inquisition for more than 15 years, culminating in his arrest, trial, conviction, and execution by burning at the stake in Rome in 1600. It is alluring to idealize Bruno solely as a scientific martyr, contending for truth against a dogmatic regime, particularly since some of his cosmological concepts and notions of a plurality of worlds have proven accurate. However, previous individuals and contemporaries, notably Galileo, had espoused beliefs contrary to the Church without facing such severe consequences. Bruno's death may have been more attributable to his confrontational demeanor and fervent critique of authority and prevailing beliefs than to his Copernican views. The prevalent misconception is that the Italian astronomer Galileo Galilei invented the telescope. Although Galileo Galilei developed an astronomical telescope with unparalleled resolution for his era, he utilized it for several years before making discoveries that conclusively affirmed the heliocentric structure of the solar system. The fundamental principles and elements originate from antiquity. The initial telescopes were termed refracting instruments, as they employed combinations of concave and convex glass lenses to refract and enlarge, or reduce, in the case of the earliest microscopes, the field of vision. The Egyptians in the 5th century BCE and Greek and Roman scholars were aware that curved, transparent surfaces could magnify images. It is believed that China or the Arab world invented glass lenses for spectacles to correct poor vision in the 11th century, or perhaps earlier, and subsequently introduced them to the West in the late 1200s. The production of spectacles was prevalent in late medieval and early Renaissance Europe. Within that context, a minimum of 3 Dutch artisans and lens manufacturers may have independently developed instruments, circa 1604 to 1608, that we now refer to as telescopes. Hans Lippershey, Zacharias Janssen and Jacob Metius engineered rudimentary nested tubes, telescopes, incorporating two lenses that provided 2 times to 3 times magnifications of a limited field of view. The Dutch awarded Lippershey a patent for his design, resulting in his common recognition as the telescope inventor, despite ongoing debates regarding the accurate historical account. In 1609, rudimentary telescopes commenced rapid sales throughout Europe. Due to the simplicity of the design and the accessibility of lenses, astronomers such as Galileo and Thomas Harriot commenced experimenting with and improving the invention, directing it skyward. In late 1609, Galileo constructed a telescope with a magnification of approximately 20 times, enabling him to observe celestial details previously unseen, thereby revolutionizing astronomy. This 19th-century artwork by French artist Henri-Julien Destouches, 1854 to 1913, illustrates Galileo showcasing an early iteration of his newly developed astronomical telescope to the Duke of Venice, Leonardo Donato, in 1609, Galileo's sidereal messenger. Revolutions frequently originate from a singular, crucial event that catalyzes the emergence of a comprehensive movement. The scientific revolution, an ongoing movement, was arguably initiated by the 1610 publication of Sidereus Nuncius, Starry Messenger, by the Renaissance Italian physicist, mathematician, and astronomer Galileo Galilei. The Starry Messenger transformed the trajectory of astronomy. The inaugural and most superior astronomical telescope, constructed by Galileo, enabled him to examine the cosmos with unparalleled clarity. He was the inaugural individual to observe and monitor Jupiter's satellites, and he discerned that not all celestial bodies revolve around the Earth. He was the first to observe the phases of Venus, thereby concluding that it orbits the Sun rather than the Earth. He was the first to discern that the Moon possesses mountains, craters, and valleys, rather than being a flawless celestial sphere. Galileo's observations and subsequent analyses in Starry Messenger directly contradicted the geocentric cosmology of Aristotle and Ptolemy. They presented persuasive evidence, albeit not conclusive proof, of Copernicus's heliocentric cosmology. For Galileo, it constituted sufficient evidence. He persisted in making observations with increasingly powerful telescopes, documenting the disks and characteristics of the planets and delineating the Milky Way into innumerable densely clustered stars. Utilizing his telescopes, he and his contemporaries were able to observe stars with magnitudes as faint as 8 or 9, which are over 15 times dimmer than those perceivable by the human eye. Galileo examined the phases of Venus. He possessed influential allies within the Roman Catholic Church who initially endorsed his findings. However, Giordano Bruno's execution demonstrated that the Church ultimately perceived Copernicanism as a menace. The Church spared Galileo but subjected him to house arrest for the final 9 years of his life. Galileo's illustration from January 8, 1610, portrays Jupiter's 4 luminous satellites, with the red arrow indicating Io's location that evening. On January 7, 1610, when Galileo first directed his telescope at Jupiter, he observed what he referred to as 3 fixed stars, completely imperceptible due to their diminutive size. These stars were positioned adjacent to Jupiter, 2 on one side and 1 on the opposite, all aligned in a straight line traversing the center of Jupiter's disk. Envision his astonishment upon observing 4 diminutive stars the subsequent night, aligned in a straight line instead of 3. Over the subsequent weeks, he observed the diminutive stars shifting about the planet. He quickly discerned the pattern. They were orbiting Jupiter. Galileo discovered 4 new celestial bodies, the first recognized moons of a planet other than Earth. He acquired the privilege to name them due to his role as their discoverer. In a politically shrewd maneuver, he designated them the Medicean stars in honor of his benefactor and financial supporter, Cosimo II de' Medici. Other contemporary astronomers detested the concept. The German astronomer Simon Marius, who asserted he discovered the moons before Galileo, proposed names derived from Greek mythology: Io, a nymph seduced by Zeus, Europa, Ganymede, and Callisto. Galileo rejected alternative nomenclature and ultimately designated the moons Jupiter 1 through 4. Astronomers employed those designations well into the 20th century. However, Marius's poetic nomenclature ultimately prevailed. They are now collectively designated as the Galilean satellites in tribute to their discoverer. Io, pronounced I-O, is the nearest of Jupiter's 4 major moons, with an orbital period of approximately 42 hours. 7 space missions, Pioneers 10 and 11, Voyagers 1 and 2, Galileo, Cassini, and New Horizons, have examined it in detail, disclosing a diameter of 2,275 miles, 3,660 kilometers, marginally larger than Earth's moon, and an unexpectedly rocky density of 3.5 grams per cubic centimeter. The most significant revelation was Voyager 1's identification of active volcanoes on Io, which adorn the moon's surface with red, orange, and black sulfur, silicate lava, and a tenuous sulfur dioxide atmosphere. Intense tidal forces induce perpetual eruptions on Io, rendering it the most volcanically active body in the solar system. Galileo's illustration from January 8, 1610, portrays Jupiter's 4 luminous satellites, with the red arrow indicating Europa's location that evening. Another small star that Galileo identified orbiting Jupiter is Europa, named after a princess who adored Zeus, the Greek counterpart of the Roman god Jupiter. On January 7, 1610, Galileo observed Io and Europa as a singular star. By the subsequent night, their movement allowed him to identify them as 2 distinct entities. Europa is the second nearest Galilean moon to Jupiter, completing an orbit around the planet in approximately 3.5 days. Galileo devised a technique to precisely forecast the trajectories of Europa, Io, Ganymede, and Callisto, suggesting the utilization of their relative positions and the timing of their periodic eclipses as a natural celestial chronometer for ascertaining longitude. Explorers such as Lewis and Clark effectively employed Galileo's technique, which was validated by the Italian-French astronomer Giovanni Domenico Cassini in 1681. Data from the 7 robotic space probes that have explored the Jovian system indicate that Europa is the smallest of the 4 major moons, possessing a diameter of 1,950 miles, 3,140 kilometers, marginally smaller than Earth's moon. The mean density of a planetary body can be estimated by dividing its mass, ascertained from the gravitational influence it exerts on a passing space probe, by its volume, determined through photographic analysis. Europa's density of approximately 3 grams per cubic centimeter is predominantly rocky, notwithstanding its icy exterior. The surface exhibited a high degree of smoothness, was relatively youthful, exhibiting few impact craters, and was fragmented into numerous disordered plates that appeared to have undergone tectonic movement about one another. Reddish fissures and lines intersected the surface. The surface closely resembles sea ice. Numerous lines of evidence indicate the presence of a substantial liquid ocean beneath a relatively thin, icy crust on Europa. The potential existence of an additional ocean within our solar system, heated by tidal forces and shielded from Jupiter's intense radiation, suggests that Europa could serve as another habitat for life. Ganymede. Galileo's illustration from January 8, 1610, portrays Jupiter's 4 luminous satellites, with Ganymede's location indicated by the red arrow that evening. The third of Galileo's newly discovered moons in 1610 is Ganymede. Named after the mythological prince, cupbearer of the gods, and lover of Zeus, It is the only moon of Jupiter named after a male figure. Ganymede requires slightly over 7 days to complete one orbit around Jupiter. Galileo and other astronomers determined the exact orbits of Io, Europa, and Ganymede, observing a notable phenomenon. For each complete orbit of Ganymede, Europa completes 2 orbits, while Io completes 4 orbits. Astronomers characterize the satellites as being in resonance, identifying the 4 to 2 to 1 orbital resonances among the 3 inner Galilean satellites, incited a minor revolution among mathematicians and physicists, endeavoring to comprehend and elucidate the origins of these resonances. The French mathematician and astronomer Pierre-Simon Laplace formulated essential explanations, and in recognition of his contributions we now refer to these types of 3-body configurations as Laplace resonances. Researchers have identified that orbital resonances generate gaps in the primary asteroid belt and Saturn's rings, and they are also observed in certain newly discovered extrasolar planets. Numerous robotic spacecraft have meticulously examined Ganymede, establishing it as the largest moon in the solar system, with a diameter of 3,275 miles, 5,270 kilometers, surpassing Mercury. The 1.9 grams per cubic centimeter density indicates that Ganymede possesses a markedly greater proportion of ice than Io and Europa. Brighter, ice-rich grooves and ridges on Ganymede's surface, likely a consequence of historical tectonic activity, seem younger than the darker, more heavily cratered regions. Ganymede is the sole moon in the solar system with a distinct, albeit weak, magnetic field, suggesting that its interior has transformed into a crust, mantle, and molten iron core. The magnetic measurements, saline minerals on the surface, and indications of past water eruptions in grooves and ridges may all suggest that Ganymede possesses a substantial layer of liquid water, an additional ocean. Callisto. Galileo's illustration from January 8, 1610, portrays Jupiter's 4 luminous satellites, with the red arrow indicating Callisto's location that evening. Callisto is the most distant Galilean moon orbiting Jupiter, named after a Greek mythological nymph and consort of Zeus. In early 1610, Galileo directed his astronomical telescope towards the giant planet, discovering Callisto and Jupiter's other prominent moons. Callisto is the most distant of Jupiter's 4 principal satellites, requiring nearly 17 days to complete a single orbit. Consequently, it does not engage in the resonances that define the orbits of Io, Europa, and Ganymede. For over 350 years following their discovery, astronomers could not acquire further knowledge regarding Callisto and the other Galilean satellites. Beginning in the 1960s, it became feasible to utilize spectroscopy from terrestrial telescopes to ascertain their surface compositions. We found that water ice predominated on Callisto, Ganymede, and Europa surfaces, whereas sulfur characterized the colors and spectra of the arid Io. Recent spectroscopic analyses from space missions have disclosed the existence of carbon dioxide and sulfur dioxide ice on Callisto and Ganymede, and hydrated sulfate salts on all 3 icy moons. These missions have also enabled us to ascertain Callisto's diameter, 2,995 miles, 4,820 kilometers, which is 25% larger than our moon, and its density, 1.8 grams per cubic centimeter, predominantly ice with some rock. They have also assisted us in delineating the features on its surface. Callisto is the most extensively cratered of the Galilean satellites, retaining large impact basins from the late heavy bombardment of the early solar system, indicating that it has experienced the least internal activity or resurfacing history among the 4. Nonetheless, information from NASA's Galileo-Jupiter mission indicates a different conclusion. The orbiter indicates the potential existence of a subsurface layer of liquid water, an ocean situated beneath the damaged icy crust. Nonetheless, Callisto lacks the tidal flexing and heating that other moons undergo due to their resonant orbital interactions or proximity to Jupiter, rendering the heat source responsible for Callisto's potential subsurface ocean enigmatic. Orion Nebula identified. The universe comprises atoms and molecules occasionally aggregating into gas, dust, and rock in peculiar and exquisite configurations. Astronomers can explore and catalog the universe by identifying regions where gas and dust are sufficiently warm and dense to emit luminescence. These locations are interstellar clouds, the ethereal, nebulous, filamentous remnants of deceased and dying stars, simultaneously serving as cocoons and nurseries for nascent stellar embryos. Upon the demise of stars in nova or supernova events, they expel their outer layers of hydrogen, helium, and various other materials into the vastness of space. Energy from proximate stars or the explosions that expelled them can frequently ionize these ejected remnants. Ionized gases in interstellar clouds emit light and heat, enabling astronomers to observe and analyze them with spectrometers and large telescopes. The Orion Nebula is a prominent interstellar cloud. It is a luminous patch observable to the unaided eye, situated beneath the trio of stars in Orion's belt. Although certain archaeological evidence indicates that ancient Mayan astronomers may have observed the nebula, French astronomer Nicolas-Claude Fabry de Peiresc first documented its observation in 1610, albeit without any subsequent report. Christian Huygens and Charles Messier rediscovered it in 1656 and 1769, respectively. Recent observations indicate that the Orion Nebula is the nearest interstellar cloud to Earth, approximately 1,340 light-years. Its composition is notably intricate, comprising hydrogen, carbon monoxide, water, ammonia, formaldehyde, and basic precursors to amino acids. Interstellar clouds serve as sites for stellar formation, where accumulations of gas and dust gradually coalesce and collapse under gravitational forces. This process is akin to the formation of the Orion Nebula from earlier generations of nearby stars. A substantial solar nebula of gas and dust gave rise to our solar system and potentially others nearby. Astronomers can generally be categorized into two groups: observationalists, who primarily gather data from telescopes or space missions, and theorists, who focus on developing models or theories to elucidate existing observations. From antiquity to the Middle Ages, the majority of astronomers and astrologers were primarily observationalists who engaged in theoretical exploration. Theoretical astronomy was predominantly regarded as the domain of philosophers rather than physicists. Johannes Kepler, a Renaissance German mathematician, astrologer, and astronomer, transformed that paradigm and is arguably the world's inaugural theoretical astrophysicist. Kepler collaborated with data from others, particularly Tycho Brahe and Galileo, to formulate a comprehensive cosmos model. Profoundly devout, Kepler posited that God had orchestrated the universe according to an elegant geometric schema which he could deduce through meticulous observations. Kepler endorsed Copernicus's heliocentric cosmology, asserting that a sun-centered solar system aligned with biblical texts. Kepler's work, Astronomia Nova, New Astronomy, 1609, delineated the elliptical orbits of Mars and other planets, first law, and posited that the planets vary in velocity, enabling them to sweep out equal areas in equal intervals of time during their orbits, second law. Subsequently, in Harmonices Mundi, Harmony of the Worlds, 1619, he demonstrated that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. P squared is proportional to a cubed. Third law. Kepler's perseverance ultimately unveiled the harmony he desired among the celestial bodies. Kepler's laws received extensive recognition when astronomers validated their precise timing forecasts during eclipses and planetary transits. In 1687, Isaac Newton discovered the inherent implications of a universal law of gravitation. Johannes Kepler sought to uncover divine perfection in the orbits of known planets by correlating them with the geometries of the so-called perfect solids, depicted in this illustration from his work Mysterium Cosmographicum, 1596. The regular polyhedra include the cube, tetrahedron, octahedron. Astronomers define a transit as an occurrence where one celestial body obscures another from the observer's perspective. A solar eclipse occurs when the moon transits across the sun's disk. Galileo and other astronomers utilized the transits of the Galilean satellites across Jupiter's disk to enhance orbital predictions and ascertain an observer's longitude on Earth. During Venus's infrequent transits across the Sun, Johannes Kepler discerned that terrestrial observers could employ parallax and trigonometry to ascertain the distance from Earth to the Sun, referred to as an astronomical unit, AU. Aristarchus, Ptolemy, and Arabic astronomers approximated the Sun's astronomical unit, AU, to be approximately 20 times the distance to the Moon, equating to roughly 5 million miles, 8 million kilometers. Due to the slight tilt of Venus's orbit about Earth, transits of Venus are infrequent, occurring fewer than once per century. In 1032, the Persian astronomer Abu Ala ibn Sina recorded a transit of Venus. Kepler forecasted a transit for 1631 and a close approach for 1639. The 1631 event did not occur in Europe. English astronomer Jeremiah Horrocks employed revised calculations to forecast and accurately document the Venus transit of December 4, 1639, utilizing the data to approximate the astronomical unit as approximately 60 million miles or 96 million kilometers. Despite his calculation being 35% lower than the actual value, 93 million miles, 150 million kilometers, Horrocks immediately enlarged the solar system to approximately 250 times its previously measured size. Captain James Cook traveled to Tahiti as part of a global initiative to observe the 1769 Venus transit, leading to a significantly more precise calculation of the astronomical unit, AU. Contemporary astronomers and millions of individuals in the general populace witnessed two recent transits of Venus across the Sun on June 8, 2004, and June 5, 2012. The subsequent occurrence is not anticipated until 2117. The Mars exploration rovers of NASA have recorded transits of Phobos and Deimos from Mars's surface, while extrasolar planet hunters have identified transits in other solar systems utilizing ground-based telescopes and satellites, including NASA's Kepler mission. Hipparchus, Ptolemy, and Al-Sufi's initial star catalogs documented numerous luminous stars that seemed close to the sphere. Notable are the bright blue stars located second from the end of the Big Dipper's handle, designated Mizar and Alcor by Arabic astronomers, frequently referred to as the Horse and Rider. These two stars, positioned approximately 1/5 of a degree apart, test the visual acuity of the human eye. Could you detach the equine from the equestrian? Early astronomers were deliberating whether such pairs of stars were interconnected or merely coincidentally proximate. The introduction of the telescope enabled the resolution of what came to be identified as genuine multiple star systems. Galileo seemingly discovered that Mizar is a binary star with a dimmer companion, Mizar B, located merely 14 arc-seconds away, necessitating a telescope for observation. Galileo refrained from publishing his discovery, possibly because Mizar A and B did not exhibit the anticipated parallax shifts that would validate Copernicus's heliocentric theory, as he and others believed the stars were significantly closer to Earth than they actually are. Thus, Italian astronomer Giovanni Riccioli, who published his findings on Mizar A and B in 1650, is frequently acknowledged for the discovery of Mizar as the first recognized double star. Nonetheless, the Mizar system proves to be even more intriguing than previously anticipated. Astronomers identified Mizar A, a double star with a companion, as a spectroscopic binary in 1889, detectable solely through the analysis of the combined spectrum of the duo. In 1908, researchers identified Mizar B as a spectroscopic binary. Mizar is a quadruple star system composed of 4 stars. In 2009, researchers identified Alcor, Mizar's visible companion, as a binary system, and recent findings indicate that Mizar and Alcor may be gravitationally bound, thereby converting the Mizar-Alcor system into a sextuplet of 6 interconnected co-orbiting stars. As inhabitants of a single star system, we find this remarkable. However, estimates indicate that approximately 60% of all stars in the galaxy are part of multiple star systems. Titan. Galileo's starry messenger of 1610, which revealed the discovery of Jupiter's 4 moons, the phases of Venus, and the existence of mountains and valleys on the moon, elicited significant enthusiasm and sparked a form of space race among 17th century astronomers. If Galileo's rudimentary spyglass could yield such discoveries, what new marvels could more advanced telescopes reveal? Subsequently, larger telescopes commenced extending their reach deeper into the cosmos. Saturn orbits the Sun at a distance nearly double that of Jupiter, resulting in sunlight being over 3 times less intense than that received by Jupiter. Unsurprisingly, it was not until 1655 that telescopes attained the sensitivity required to perceive the faint sunlight reflected from a moon orbiting Saturn. Christian Huygens, a Dutch astronomer, made that discovery utilizing a telescope of his own design. Huygens designated the new moon Saturni Luna, Latin for Saturn's moon. It was not until 1847 that it was named Titan, following a Greek mythology theme for the nomenclature of the 7 known satellites of Saturn at that time. Contemporary explorations of Titan by the Voyager and Cassini space missions have unveiled an unusual and distinctive realm. Titan, the 2nd largest moon in the solar system, measuring 3,200 miles, 5,152 kilometers, in diameter, surpassing the size of the planet Mercury. Titan's 1.9 grams per cubic centimeter density suggests a composition of ice and rock in its interior. The sole moon possesses a substantial atmosphere, a dense amalgamation of nitrogen and methane fog that obscures the surface from observation. We anticipate that hydrocarbons formed by sunlight in Titan's nitrogen-methane atmosphere will exist as liquids, given its temperature of 90 kelvins and a surface pressure approximately 50% greater than Earth's. The Cassini orbiter's radar mapper discovered rivers and lakes of liquid ethane or propane on Titan. The environment of Titan is devoid of oxygen, leading to slow organic chemistry processes. It is a prominent site for astrobiology, the optimal location in the solar system to investigate the conditions of early Earth before the enrichment of our atmosphere with oxygen due to life. In 2005, Titan received the inaugural probe to land on its surface. The mission was aptly designated Huygens. In 1610, Galileo was the first to observe Saturn through a telescope. Utilizing his modest astronomical telescope, the planet manifested as a circular disk with 2 luminous protrusions on either side, which he called ears. Galileo endeavored to comprehend the nature of these features throughout his lifetime, which fluctuated in visibility over time. In 1659, Dutch astronomer Christian Huygens utilized his enhanced telescope to observe Saturn, becoming the inaugural individual to identify the ears as a disk or thin, flat ring encircling the planet. In 1675, the Italian-French mathematician and astronomer Giovanni Domenico Cassini identified a dark gap in the rings, now called the Cassini division. They propose that the rings consist of a sequence of narrower, distinct ones. Before the hypothesis of Scottish physicist James Clerk Maxwell, which posited that gravitational and centripetal forces would disintegrate solid rings, astronomers and mathematicians regarded the rings as solid disks. The Voyager 1 and 2 flybys of Saturn's rings in the 1980s corroborated Maxwell's theory. In conjunction with the Cassini-Saturn orbiter, the flybys revealed that the rings consist of numerous distinct ringlets composed of dust-sized to house-sized particles, predominantly of nearly pure water ice, along with some silicate dust and potentially simple organic molecules. The primary rings measure 174,000 miles, 280,000 kilometers, in width, yet possess a remarkably minimal thickness of less than 328 feet, 100 meters. Gravitational interactions with minor moons orbiting within the rings have significantly diminished ring particles, forming gaps in the rings. Planetary scientists discuss the genesis and antiquity of Saturn's rings. Are they primordial or young, potentially formed merely a few 100 million years ago due to the catastrophic disruption of an icy moon? In the 17th century, scientists Robert Hooke and Giovanni Domenico Cassini utilized their early astronomical telescopes to observe Jupiter, becoming the first to identify and monitor a circular reddish scar in the planet's southern hemisphere. They could scarcely conceive that they were monitoring a colossal hurricane-like storm system exceeding twice the size of Earth, which would persist in its tumultuous activity for nearly 350 additional years, if not longer. Astronomers and planetary scientists have examined Jupiter's Great Red Spot more precisely using contemporary telescopes and space missions. Scientists recognize the Great Red Spot as a persistent, counterclockwise rotating atmospheric vortex. The time-lapse photography of the storm's rotation indicates that it requires approximately 6 Earth days, around 14 Jupiter days, for a complete spin. Wind velocities reach approximately 270 miles per hour, 430 kilometers per hour, at the storm's periphery, where it engages with various belts and regions within Jupiter's atmosphere. The Great Red Spot is cooler than the adjacent regions of Jupiter's atmosphere because its storm clouds are approximately 6 miles, 10 kilometers, higher than the surrounding clouds. Should we traverse that region of Jupiter's atmosphere, we would observe a colossal, gradually rotating cumulonimbus cloud ascending above the obscurity. Intense jet stream winds to the north and south of the Great Red Spot supply the energy necessary to maintain the storm's confinement at a consistent latitude. Although the size of the spot has diminished somewhat over the past few decades, the duration of its continued activity remains undetermined. The reason for the red coloration of the Great Red Spot remains enigmatic. Diverse hypotheses propose that atmospheric gases or aerosols comprising sulfur, phosphorus, or organic compounds induce the coloration. Astronomers have noted the color transformation of the spot over the past few decades, shifting from reddish to brownish, yellowish, and even whitish. The investigation into the origins of the Great Red Spot's color and the hues of Jupiter's other striking atmospheric patterns constitutes a dynamic field of planetary science research. The enigma surrounding the origin and future of the spot further accentuates the Van Gogh. Its vibrant swirling clouds are a testament to beauty. Stars originate from the gravitational collapse of vast clouds of gas and dust. Astronomers have discovered that these clouds are frequently sufficiently large for multiple stars to originate from a single cloud or a cluster of closely associated clouds. This generates numerous star systems and regions where star formation accelerates, such as the arms of a spiral galaxy. Certain interstellar clouds, particularly in the primordial universe, have been sufficiently massive to facilitate the formation of hundreds of thousands of stars nearby. A globular cluster is an assemblage of stars formed through gravitational interactions that aggregate them into a spherical mass, orbiting a shared center of gravity, potentially including a black hole. In 1665, Johann Ille, a German postal official and enthusiastic amateur astronomer, conducted the inaugural telescopic observations of a globular cluster. In astronomer Charles Messier's catalogue, Ille observed a dense cluster of stars, currently designated as M22, or the Sagittarius cluster. M22 presents itself as a subtle fifth-magnitude blur to the unaided eye. Ille and other 17th-century astronomers utilized their telescopes to demonstrate that the streak is the aggregated light of many densely clustered stars. Since that time, researchers have identified over 150 luminous, densely concentrated globular clusters, such as M22, orbiting the core of our Milky Way galaxy, which is encompassed by a semi-spherical halo of stars and star clusters that predate the average stars located in the galactic disk. Researchers have identified globular cluster halos in other galaxies, indicating that halo formation is pivotal in the early development of galaxies. Globular cluster halos extend extensively from the centers of numerous galaxies, leading astronomers to hypothesize that some galaxies exchange star clusters during gravitational interactions or close encounters. Stars within globular clusters interact with proximate neighbors significantly more often than stars in typical interstellar environments. Consequently, astronomers do not consider globular clusters favorable locations for the discovery of stable, habitable planets. Nevertheless, a significant amount remains undiscovered regarding these ancient stellar clusters. The identification of Jovian moons in 1610 and a moon orbiting Saturn in 1655 ignited a fervor for lunar exploration among late 17th century astronomers. Giovanni Domenico Cassini, the prolific Italian-French mathematician and astronomer, identified the solar system's sixth and seventh moons in 1671 and 1672, naming them after the Greek titan Iapetus and his mother, Rhea. Cassini could observe Iapetus solely on Saturn's western hemisphere. It became obscured as the planet rotated to the eastern hemisphere. In 1705, Cassini ultimately observed the moon on the opposite side of Saturn, despite it being over 6 times dimmer. Cassini and others hypothesized that akin to our moon, Iapetus is tidally locked, consistently presenting the same face to its parent planet. Consequently, one hemisphere of Iapetus orients forward in its trajectory, the dark leading side, while the opposite hemisphere consistently faces backward, the bright trailing side. Rhea was similarly challenging to detect. It orbits 50% nearer Saturn than Titan. The discovery's proximity to Saturn's disk glare exemplifies Cassini's observational skill and the advancements in telescope and optical technology during the late 17th century. A ridge of indeterminate origin, measuring 12.4 miles, 20 kilometers, in height, encircles a significant portion of Iapetus's equator. The Voyager missions in the 1980s provided closer observations of Iapetus, revealing its peculiar two-toned surface and an ice-like density of approximately 1.1 grams per cubic centimeter. In-depth investigations conducted by the Cassini Orbiter mission have disclosed that Iapetus possesses an archaic, extensively cratered surface and an equatorial ridge that imparts a walnut-like morphology to the moon. Voyager provided a close-up view of Rhea, revealing it to be bright, with reflectivity exceeding 50%, extensively cratered, and an ice-like composition. What accounts for Iapetus's peculiar dichromatic surface? Phoebe, the adjacent moon, and the origin of a faint outer ring of Saturn may be the cause. The leading hemisphere of Iapetus might have darkened initially while traversing through Phoebe's ring dust. Christian Huygens, 1629–1695, and Ole Christensen Remmer, 1644–1710. Throughout history, individuals have contested the essence of light. The Greek philosophers Aristotle, Euclid, and Ptolemy posited that light emitted from the eyes must travel at an infinite velocity, as we perceive distant objects such as stars instantaneously upon opening our eyes. In the 11th century, scientists such as the Muslim physicist Al-Haytham and the Persian scholar Al-Biruni posited that light possessed a finite speed, drawing conclusions from preliminary optical experiments. The discourse persisted into the 17th century, with prominent figures such as Kepler advocating for infinite speed and Galileo supporting finite speed. A conclusive measurement was required. Ole Christensen Remer, a Danish astronomer, refined Galileo's initial idea of utilizing Jupiter's moons as astronomical clocks, not for determining longitude but for measuring light time, culminating in the inaugural accurate estimation of light speed. Remer meticulously recorded numerous eclipses of Jupiter's moon Io, precisely timing its obscuration and emergence from Jupiter's shadow. He observed that the forecasted eclipse times consistently deviated from the recorded times. They transpired approximately 11 minutes earlier when Earth was nearest to Jupiter, and 11 minutes later when Earth was farthest from it. Remer ascribed the discrepancy to the finite speed of light. Assisted by his Dutch colleague Christian Huygens, Remer approximated the speed of light from his eclipse data to be around 137,000 miles per second. Enhanced measurements of stellar aberration by English astronomer James Bradley in the 18th century and the Michelson-Morley experiment in the 19th century indicated that the actual value was approximately 35% greater. His acumen and extensive observation culminated in the inaugural accurate estimation of the speed of light. Halley's Comet. Edmund Halley, 1656 to 1742. Comets are infrequent, often striking intruders within the otherwise predictable order of the solar system. Early Chinese astronomers designated them broom stars due to their elongated tails. Isaac Newton hypothesized that at least some revolve around the sun, although he did not endeavor to substantiate the concept. However, Newton's associate and compatriot Edmund Halley, an English astronomer, geophysicist, and mathematician, promptly embraced the concept. Halley observed a luminous comet in 1682. Subsequently, by analyzing historical records and applying Newton's laws to compute its trajectory, he posited that it was the identical comet witnessed in 1531 and 1607. These 76-year intervals enabled him to forecast the comet's return in 1758. Indeed, although Halley did not witness its return, astronomers designated it Halley's Comet, now simply Halley, in his tribute. The comet was subjected to more sophisticated telescopic and photographic analyses during its 1835 and 1910 appearances. The Soviet Vega and European Giotto probes approached Halley's central nucleus in 1986. The object was unexpectedly diminutive, approximately 9 times 5 times 5 miles, 15 times 8 times 8 kilometers, peanut-shaped, coarse, porous, with a density of roughly 0.6 grams per cubic centimeter, and as dark as coal. Vivid jets of ice consisting of water, carbon monoxide, and carbon dioxide emerge from the surface and interior, expelling dust and organic molecules, thereby forming an elongated tail. Halley was identified as the inaugural periodic comet. Approximately 500 additional short-period comets, with orbital periods under 200 years, are currently identified. The majority originate from the Kuiper belt, situated beyond Neptune, although some, such as Halley, may have originated as long-period comets from the remote Oort cloud. Astronomers have determined that more than 20 luminous comets documented between 240 BCE and 1682 CE were all prior appearances of Halley's Comet. The subsequent passage is scheduled for the summer of 2061. Tethys and Dione. After discovering Saturn's moons, Iapetus and Rhea, in 1671 and 1672, astronomer Giovanni Domenico Cassini persisted in his search for fainter moons, employing increasingly advanced telescopes at the Paris Observatory. In 1684, he identified the fourth and fifth known moons of Saturn, subsequently named Tethys, after the Greek sea goddess, and Dione, after the mother of Aphrodite, utilizing a tubeless, or aerial telescope, measuring 100 feet, 30 meters, in length. Limited information existed regarding these two new moons beyond their fundamental orbital characteristics until spectroscopic analyses in the 1970s disclosed the existence of water ice on their surfaces. Subsequently, spacecraft mission encounters disclosed that they were distinct worlds. Images from the Voyager and Cassini space missions revealed that Tethys has a diameter of approximately 670 miles, 1,080 kilometers, about 30% the size of Earth's moon, and features a highly reflective, heavily cratered surface. The moon demonstrates significant reflectivity and has a density of 0.97 grams per cubic centimeter. The principal composition of Tethys is aligned with water ice. Tethys features striking icy terrains, including a vast impact basin called Odysseus, 400 kilometers wide, and a colossal valley known as Ithaca Chasma, 100 kilometers wide and 3 to 5 kilometers deep, which spans approximately 75% of the moon's circumference. Images of Dione revealed that it is an ice-covered celestial body, comparable in size to Tethys, featuring icy cliffs reaching hundreds of meters in height. Dione's primordial, extensively cratered surface exhibits a variable density of craters across different regions. This indicates that certain regions of the moon may have undergone early resurfacing, potentially due to liquid water volcanoes emanating from a heated interior and depositing younger ice lava flows over older surface regions. Dione possesses a greater density than most of Saturn's other moons, approximately 1.5 grams per cubic centimeter, suggesting a more substantial rocky interior. Radioactive decay from this rocky composition may have generated the heat necessary for water ice volcanism. Zodiacal light. Both experienced and novice astronomers recognize that optimal night sky observation occurs on a clear, moonless night at a remote location, away from urban illumination. Nevertheless, the sky remains partially illuminated. Alongside the myriad visible stars and the Milky Way galaxy's nebulous luminescence, one frequently perceives an additional subtle radiance, especially in the west post-sunset or the east pre-sunrise. This phenomenon is termed the zodiacal light due to its manifestation as a pale band or subtle spire on the horizon, positioned away from the sun and approximately aligned with the trajectory of the zodiac constellations. The ecliptic, the plane of the sun's equator, and the trajectories of most planets in the solar system are also denoted by this line. Islamic astronomers designated the zodiacal light as the false dawn. Comprehending its characteristics and impact on accurately determining true sunrise or sunset was crucial for establishing the timing of daily prayers. Numerous Renaissance astronomers, such as Giovanni Domenico Cassini, who observed the luminous streak in 1683, posited that it was merely an extension of the sun's atmosphere. A conundrum persisted regarding the reason for the brightness solely along the sun's equatorial plane. Nicolas Fatio de Duillier, a Swiss mathematician who collaborated with Cassini at the Paris Observatory, was the first to propose an accurate explanation. Particles reflecting sunlight produce the glow. Contemporary spectroscopy and space probes have validated Fatio's theory. The zodiacal light originates from sunlight reflecting off interplanetary dust particles. These grains are diminutive, measuring approximately 100 microns in width, comparable to the diameter of a human hair. As these grains gradually spiral toward the sun due to sunlight absorption, a phenomenon known as pointing Robertson drag requires a continuous source to replenish them. Astronomers contend that dust from comets and sporadic collisions among asteroids, predominantly traversing the ecliptic, constitute a persistent source of cosmic dust. Origins of tides. Throughout history, coastal communities and maritime civilizations have attuned themselves to the tides, the bi-daily oscillation of the sea. Babylonian and Greek astronomers acknowledged the correlation between tidal height and the moon's orbital position. They posited that nearly equal spiritual forces that regulated the movements of the planets also linked them. Early Arabic astronomers posited that variations in sea temperature affected tidal movements. In support of heliocentrism, Galileo posited that tides result from the oscillation of the oceans due to the Earth's movement around the Sun. Isaac Newton, the English mathematician, physicist, and astronomer, was the first to accurately propose the origin of the tides connecting the Earth, Moon, and Sun. In addition to various pursuits, Newton was formulating a comprehensive theory to elucidate Kepler's laws of planetary motion, and by 1686, he had established the foundational framework for new theories of universal gravitation and the laws of motion. Newton posited that the Moon and the Sun exert significant gravitational forces on the Earth, and conversely. His significant discovery, subsequently validated and expanded upon by space observations, revealed that the tides are primarily induced by gravitational forces exerted on the Earth's thin, fluid oceanic shell, rather than its rotation or orbital motion. The Moon's gravitational pull generates a deep water ocean tide of approximately 20 inches, 50 centimeters, while the Sun's tidal influence is roughly half that magnitude. Tidal heights in shallow water can increase by up to 10, and the tides at specific coastal locations are significantly influenced by the Sun and Moon positions, in addition to the local seafloor depth and coastline configuration. The solid components of the Earth and Moon also exhibit bulging due to gravitational tidal forces, with an amplitude generally around 50% of that observed in oceanic tides. Solid and liquid deformation dissipates energy in the Earth-Moon system via tidal friction. The Earth's rotation is decelerating by several milliseconds per century, while the Moon is gradually distancing itself from the Earth by approximately 13 feet per century. Sir Isaac Newton posits a gravitational relationship among the Moon, Earth, and Sun. Each exerts significant gravitational attraction on the other, proportional to their masses and inversely proportional to the square of their distances. The dynamic characteristics of Earth's oceans enable these forces to manifest as tides. Newton's laws of gravitation and motion. The scientific revolution initiated by Aristarchus, who suggested displacing the Earth from its central cosmological position, was perpetuated for 2,000 years by scientific dissenters, including Aryabhata, Bruno, Nalakantha, Copernicus, Tycho, Kepler, and Galileo. This revolution ultimately culminated in the contributions of Englishman Isaac Newton. Newton, a mathematician, physicist, astronomer, philosopher, and theologian, is regarded by many as one of the most influential scientists in human history. Newton was proficient as an experimentalist and a theorist, excelling in each domain. He innovated new concepts and instruments in optics, notably the inaugural astronomical telescope utilizing mirrors rather than lenses, a design that is eponymously attributed to him. In the theoretical realm, Newton employed fundamental concepts from modern physics and effectively formulated the new discipline of calculus to demonstrate that Kepler's laws of planetary motion result from a force that exists between any two masses, diminishing as the square of the distance between them increases. This phenomenon is referred to as 1 over r squared behavior. He designated this force as gravitas, Latin for weight. It is now referred to as gravitation, and the 1 over r squared relationship is recognized as Newton's law of universal gravitation. Newton expanded upon that foundation to formulate his 3 renowned laws of motion. 1. An object at rest or in motion remains in that state unless acted upon by an external force. 2. An object of mass, m, subjected to a force, F, will accelerate, a, according to the equation F equals ma. And 3. The forces of action and reaction between two objects are equal in magnitude and opposite in direction. In 1687, Newton disseminated his groundbreaking theories in a work recognized and esteemed today as the Principia Philosophiae Naturalis Principia Mathematica. Newton's laws of gravitation and motion obliterated any vestiges of geocentrism. For over 200 years, they represented the conclusive solutions to planetary orbits, until Albert Einstein demonstrated that they were a subset of a more comprehensive theory known as general relativity. In a renowned illustration of scientific humility, Newton stated, "If I have seen further, it is by standing on the shoulders of giants." British astronomer Edmund Halley is renowned for identifying the periodic return of Halley's Comet. He also examined various facets of astronomy, including comparing stars' positions with those documented by earlier astronomers to ascertain the nearest stars to the Sun and calculate their absolute distances. Most astronomical history posited that stars were stationary inhabitants of a crystalline or solid celestial sphere, which either revolved around the Earth, according to some, or seemed to rotate as the Earth rotated beneath it, according to others. The sporadic emergence of supernovae or comets, referred to as guest stars, raises questions about the notion of a static celestial sphere, yet it does not refute it. Halley substantiated that evidence by meticulously contrasting the positions of luminous stars in 1718 with those documented by Hipparchus in the 2nd century BCE. Over 1,850 years, three prominent stars, Sirius, Arcturus, and Aldebaran, have undergone substantial movement about the background stars. Halley computed the proper motion of these stars, referring to the intrinsic motion of the star itself instead of the apparent motion attributable to parallax. The stars exhibiting the most significant proper motion are comparatively nearer to the Sun. The three aforementioned stars are approximately 9, 37, and 65 light-years distant. Stars in proximity to the Sun, including Proxima Centauri, 4.3 light-years, and Barnard's star, 6 light-years, identified in 1916 by American astronomer E. E. Barnard, exhibit even greater proper motions. Barnard's star possesses the most significant known motion, exceeding 10 arcseconds, 0.003 degrees, annually. Halley and other pioneers of stellar astrometry have elucidated that the celestial sphere visible at night is merely a projection of an incomprehensibly vast three-dimensional spatial volume. All entities are in motion relative to one another, and, as Edwin Hubble would ascertain in the 20th century, the entire expanse is expanding over time. With sufficient patience, one can observe the dynamic nature of celestial navigation. Prior to the invention of the first astronomical telescopes, armillary spheres, celestial globes, and astrolabes were employed to ascertain the distances between stars and planets and to determine the altitude and azimuth of celestial bodies, referred to as their declination and right ascension. Constructing large and unwieldy circular instruments such as the astrolabe was essential for greater measurement precision. Consequently, astronomers and instrument manufacturers commenced utilizing exclusively semicircular segments to diminish instrument dimensions while preserving accuracy. Measuring instruments constructed from a quarter of a circle, quadrants, emerged in the mid-16th century. Tycho Brahe devised a large pedestal-mounted or framed instrument covering 1/6 of a circle, which he termed a sextant. These devices maintained unparalleled positional measurement accuracy despite the invention and widespread use of the telescope. Octants, or 1/8 circle versions, emerged in the 18th century. Framed quadrants, sextants, and octants were effective instruments on land. However, they lacked practicality at sea, where greater precision was essential. Miniaturization, adaptability, and ease of operation on a mobile platform were essential. Isaac Newton suggested altering the quadrant by incorporating two mirrors, akin to his design for the reflecting telescope. In 1757, English instrument maker John Bird constructed a portable sextant utilizing Newton's double mirror design. Contemporary sextants replicate this 18th century design, incorporating advanced optics and composite materials. Despite the prevalence of computerized systems and global positioning technology, it is encouraging that numerous mariners today must master celestial navigation with a sextant. Planetary nebulae. The introduction of telescopes in the 17th century, along with substantial enhancements in their dimensions and capacity to identify dim celestial bodies in the 18th century, facilitated remarkable discoveries by astronomers during the Enlightenment. Not only fainter stars, but also entirely new categories of objects became observable. The predominant category of stars comprised indistinct, expansive luminescent regions that resembled dim, stationary clouds. Astronomers called them nebulae, singular nebula, Latin for clouds. Ancient and medieval astronomers documented numerous luminous nebulae, including the Orion Nebula and a nebula in Andromeda. However, 20th century astronomers subsequently identified them as distinct galaxies. In 1715, Edmund Halley published a concise catalogue of nebulae. Nonetheless, the preeminent figure in 18th century nebular observations was the French astronomer Charles Messier, who compiled a comprehensive early catalogue of over 100 nebulae. In 1764, Messier identified an object and designated it M27, exemplifying a specific category of nebula. M27 and analogous objects exhibited a somewhat circular, nebulous appearance, resembling the giant planets observed through contemporary telescopes. This prompted the English astronomer William Herschel to designate them as planetary nebulae. The chosen name is notable. However, it is regrettable, as contemporary spectroscopic observations indicate that these objects are unrelated to planets. Contemporary spectroscopic observations have identified planetary nebulae as vast, expanding shells of luminous heated gases expelled from red giant stars approaching the conclusion of their stellar lifespans. Typical planetary nebulae can exceed 1 light-year in diameter, emitting light from carbon, oxygen, nitrogen, and other elements heavier than hydrogen and helium, which are produced during the collapse of their progenitor stars. Consequently, planetary nebulae constitute a cosmic recycling mechanism that transforms hydrogen and helium into heavier elements and life. Messier Catalogue. Observing remarkable celestial phenomena in his youth, including the significant comet of 1744 and the solar eclipse of 1748, ignited Frenchman Charles Messier's enduring passion for astronomy. His fervor for observation prompted him to serve in Paris as a depot clerk for the official astronomer of the French Navy, a position that involved utilizing an observatory atop the Hôtel de Cluny. Messier had sufficient observation time and an optimal dark sky location in pre-industrial revolution Paris. His initial enthusiasm was for comet hunting. He was one of the initial astronomers to confirm the anticipated return of Halley's comet in 1758 to 1759. During his search, he identified another comet and a comet-like streak of light in the constellation Taurus. In contrast to a comet, this smudge did not exhibit motion relative to the stars. He recorded it. Throughout the subsequent decade of comet hunting, he discovered numerous nebulous cloud-like formations, assigning each a designation consisting of the letter M followed by a numeral. Some, such as M22, discovered in 1665, could only be discerned as a circular cluster of densely packed stars, later termed globular clusters. Others, like M31, exhibited an elongated form and had previously been identified as a substantial nebula in Andromeda. Numerous objects were those that Messier himself was the inaugural individual to discover and delineate. By 1771, he had accumulated a collection of 45 objects, which he published as Catalogue des nébuleuses et des amas d'étoiles, Catalogue of Nebulae and Clusters of Stars, in the Journal of the French Academy of Sciences. By 1781, he and his associate Pierre Méchain, who would later become the director of the Paris Observatory, had accumulated an additional number. Their final catalogue comprised 103 objects. In the 20th century, astronomers identified 7 additional objects observed by Messier and Méchain after 1781, increasing the total count of Messier objects, now classified as star clusters, planetary nebulae, molecular clouds, and galaxies, to 110. Amateur astronomers and astronomy clubs endeavor to observe all 110 Messier objects during springtime Messier marathons. Such events may ignite a child's fascination with astronomy. Lagrange points. In his 1687 publication of the Principia, Isaac Newton augmented Kepler's laws of planetary motion into comprehensive laws of gravitation and motion, thereby creating a robust framework for astronomers, physicists, and mathematicians to comprehend the complexities of celestial movements and their underlying causes. The three-body problem is one of the most complex applications of Newton's laws. Newton's equations can be readily employed to comprehend the gravitational influences that dictate the movements of two masses, such as the Earth and the Moon, or the Sun and the Earth. The calculations became quite complex when theorists incorporated the gravitational influences of a third body. The French mathematician Joseph-Louis Lagrange was the inaugural individual to effectively resolve a particular instance of the three-body problem. In 1772, he postulated that any three-body system comprising two substantial masses and one minor mass would possess 5 specific locations where the gravitational forces among the bodies would equilibrate. These locations are now referred to as Lagrange points. The 20th century identification of the Trojan asteroids, which are captured at the L4 and L5 Lagrange points of the Sun-Jupiter system, validated Lagrange's hypothesis. The French mathematician Pierre-Simon Laplace introduced the term celestial mechanics in 1799 to characterize the physics and mathematics involved in analyzing intricate solar system movements. Lagrange's resolution of the three-body problem was comparatively simple, as it postulated that a minor object interacted with two substantial massive bodies, one in a nearly circular orbit around the other. Celestial mechanicians expanded upon Lagrange's discovery to tackle more complex three-body problems. Researchers in the 21st century often utilize high-speed computers to solve increasingly complex n-body problems. These issues necessitate monitoring the Newtonian trajectories of various entities, including planets, moons, asteroids, ring particles, and cosmic dust grains, to comprehend, elucidate, and forecast intricate movements within our solar system. Discovery of Uranus. No planet had been discovered before 1781, marking the commencement of human history. The 5 planets, excluding Earth, that are observable without optical instruments, have been recognized since prehistoric eras. Following the invention of the astronomical telescope, Galileo, Huygens, and Cassini identified new moons, but did not discover any new planets. The distinction of being the inaugural individual to identify a completely new planet was awarded to the English musician and astronomer William Herschel. Herschel's musical talents fostered an interest in astronomy and optics, prompting him to construct telescopes following his acquaintance with the English astronomer Royal Neville Maskelyne. In March 1781, Herschel observed a 6th magnitude extended object, initially believing he had discovered a comet. He monitored and documented its location, and by 1783, other astronomers confirmed that it was, in fact, a new planet orbiting at 19 astronomical units, significantly beyond Saturn. Herschel was not the initial observer of the planet, but as the first to identify it accurately, he had the privilege of naming it. He selected Georgium Sidus, George's star, in honor of King George III, yet similar to earlier celestial nomenclatures derived from patronage, it failed to endure. Astronomers subsequently designated it Uranus, pronounced Uranus, in honor of the Greek deity of the heavens. Contemporary telescopic observations and the 1986 Voyager 2 space probe flyby have identified Uranus as an ice giant planet, possessing a density of 1.3 grams per cubic centimeter, with a size 4 times and a mass 15 times that of Earth. In contrast to Jupiter and Saturn, Uranus's atmosphere is significantly less dynamic, although it is abundant in hydrogen and helium. Methane imparts a bluish-green hue, surrounding an Earth-sized, icy, rocky core. Uranus is inclined laterally, creating the illusion of rolling rather than rotating on its axis. The planet possesses 27 recognized moons, comprising 5 substantial icy bodies, 2 identified by Herschel. In 1977, starlight, flickering as it traversed Uranus, unveiled its slender, dark rings. In 2007, we traversed the plane of those rings. Astronomers are currently studying springtime on the 7th planet. Titania and Oberon. Following the discovery of Uranus in 1781, English astronomer William Herschel persistently observed the planet using progressively larger telescopes. The larger mirrors and focal lengths of his instruments enhanced their light-gathering capacity, allowing for the detection of fainter objects and improved resolution to differentiate these objects from nearby ones. Enhanced technology, meticulous observations, and support from his sister and fellow astronomer Caroline Herschel facilitated the discovery of additional moons orbiting Uranus and Saturn. Herschel identified 2 moons orbiting Uranus on a single night in early 1787. By observing their movements and presuming that the moons orbited in proximity to the planet's equatorial plane, Herschel and other astronomers swiftly inferred the significant inclination of Uranus's spin axis, referred to as obliquity. Uranus is tilted on its side, exhibiting an obliquity of approximately 98 degrees. The axial tilt of a planet is the cause of the seasons. Earth's inclination of 23.5 degrees results in the distinct seasons of winter, spring, summer, and autumn, as well as the prolonged polar days and nights experienced in the Arctic and Antarctic regions. Uranus and its moons undergo polar days and polar nights lasting 42 Earth years in the northern and southern hemispheres. Severe inclinations result in extreme seasons. John Herschel, the son of Herschel and a distinguished astronomer, ultimately designated the names of these and the other Uranian moons, selecting characters from the literary works of William Shakespeare and Alexander Pope. In homage to the Queen of the Fairies in Shakespeare's A Midsummer Night's Dream, he designated the more luminous of the 2 moons he discovered as Titania. The second was designated Oberon in honor of the Fairy King. The 1986 Voyager 2 encounter with Uranus unveiled Titania and Oberon as extensively cratered bodies, each approximately half the diameter of Earth's moon. Their comparable densities suggest rocky and icy interiors. Since that time, spectroscopy has uncovered surfaces containing water and CO2 ices, and simple organic molecules generated by the irradiation of methane or other carbon